Jet propulsion can be defined as the force which is generated in the opposite direction to that of a discharge of fluid under pressure escaping through an opening. The force that makes a lawn sprinkler, similar to the one shown here, rotate when water flows through it is one example of jet propulsion that is readily apparent in everyday life. And the thrust that sends rockets, like this one, into space is another, which is perhaps not such an everyday occurrence. Whatever the form that the device utilizing jet propulsion takes, it is essentially a reaction engine, which operates on the principle of the third law of motion, as stated by the English physicist Sir Isaac Newton in 1687, which is that every action has an equal and opposite reaction. The first recorded use of a reaction engine was by Hero of Alexandria in 250 BC. Hero's engine, a representation of which is shown here, consisted of a sphere into which steam was introduced under pressure. The steam was fed through apertures in the centre of the bearings upon which the sphere was allowed to rotate. Allowing the steam to escape through nozzles in two bent tubes mounted opposite one another on the surface of the sphere created thrust, which caused the sphere to rotate around its axis. It's alleged that Hero invented his engine while he was investigating different methods of opening the doors of a temple in Alexandria. In recent times, one of the first attempts at creating jet-powered aircraft resulted in the development of a hybrid design. An Italian, Secondo Campini, designed a system whereby an external power source, in this case a conventional piston engine, powered a compressor. The output of the compressor was mixed with fuel, the mixture of air and fuel ignited, and jet thrust resulted. Campini collaborated with the Italian aircraft manufacturers Caproni, and in August of 1940 the Campini-Caproni CC-2 flew. Although the Italians were unaware of it, a year earlier than this the Germans had flown their version of a jet aircraft, the Heinkel 178. This aircraft was powered by an engine designed by a young German scientist called Hans von Ohain. Despite the relatively sparkling performance for that era, it could travel at speeds in excess of 400 miles per hour, the German Air Force initially paid it scant regard, and it was never produced in any quantity. On the 8th of April 1941, the first official flight of the Gloucester E-2839 aircraft took place at Brockworth in Gloucestershire. Sir Frank Whittle had submitted patents for his jet engine in 1930, but it was not until 1939 that sufficient financial and technical backing was found to enable him to manufacture a flyable version of his engine. The firm of Rover had, reluctantly, initially been contracted to produce the Whittle engine, but Rolls-Royce, who could see its potential, eventually took over development of the engine, one of which is shown here. Rolls-Royce reworked the Whittle design to produce the Derwent engine, an example of which is depicted here. This engine was capable, in its Mark IV version, of producing 2,450 pounds of thrust. Later versions of the engine, capable of 3,600 pounds of thrust, were used to power the Gloucester Meteor F8, like the one shown here, flying at an open day at Royal Air Force Kemble in the year 2000. During a visit to the United States in early 1944, the leader of the Rolls-Royce design team found that General Electric were developing engines capable of producing up to 4,000 pounds of thrust. As a response to this, after his return, he initiated a project which culminated in the Nene engine, which at the time was the most powerful engine in the world, with 5,000 pounds of thrust. Possibly one of the most important but least publicized uses of this engine was its incorporation into the Russian MiG-15 aircraft, which was so effective in the Korean conflict. One critical difference between the German engines used in the Heinkel and the later Messerschmitt 262 and those developed from Sir Frank Whittle's original engine was the type of compressor employed. While the Whittle engine used a centrifugal compressor, similar to the example shown here, the German engines, like the BMW 003 model used in the Heinkel 162, utilized an axial flow compressor, similar in design to the cutaway model shown. Axial flow compressors have several advantages over the centrifugal compressor. For instance, whereas the centrifugal compressor compression ratio is limited to approximately 12:1, when the maximum of 2 stages are used in series, by adding more stages to an axial flow compressor, compression ratios as great as 40:1 can be obtained. The term compression ratio refers to the ratio of the pressure at the outlet of a compressor to that at its inlet. A second advantage of the axial flow compressor, almost as important as the first, is that the mass flow which can be obtained through an axial flow compressor is potentially much greater than the mass flow which can be achieved through a centrifugal compressor. As a consequence of these factors, the development of the early centrifugal compressor engines was subjugated in favor of the advancement of the axial flow compressor engines, which continues today. The principle of the gas turbine engine is basically the same as that of the piston engine propeller combination. They both propel a mass of air backwards. Mass times acceleration equals force. In a gas turbine engine, the mass, m, mentioned in the equation is the air delivered by the compressor. The acceleration in the equation is the difference in the outlet velocity of the air, VO, to that of its inlet velocity, V1, due to the addition of heat energy. Force equals mass times V0 minus V1, which equals thrust. With the piston engine propeller combination, the propeller drives a relatively large mass of air backwards fairly slowly, while the gas turbine throws a small mass of air backwards relatively quickly. Newton's third law states, for every force acting on a body, there is an equal and opposite reaction. In the two cases quoted earlier, the piston engine propeller combination and the gas turbine engine, the force created by the mass of air being thrown backwards and its velocity generates a reaction in the opposite direction, driving the aircraft forwards. It must be remembered that the jet reaction does not result from the pressure of the jet on the atmosphere. In all instances, the resultant reaction or thrust exerted on the engine is proportional to the mass or weight of the air expelled by the engine and the velocity change imparted to it. The working cycle of the gas turbine engine is called the Brayton cycle, after George Brayton, an American mechanical engineer who invented the continuous ignition engine, which was the basis of the gas turbine engine. The Brayton cycle and the working cycle of the four-stroke piston engine, the Otto cycle, are very similar, as can be seen in this diagram. The induction, compression, power, and exhaust strokes of the Otto cycle are each matched by induction, compression, combustion, and exhaust stages in the Brayton cycle. One major difference, however, exists in that in the gas turbine engine, combustion, theoretically, occurs at a constant pressure, whereas in the piston engine it occurs, once again theoretically, at a constant volume. Power is developed in the turbine of the engine. Other differences between the piston engine and the gas turbine engine concern the continuous manner in which these processes occur in the gas turbine engine, as opposed to the intermittent procedure occurring in the piston engine. In the piston engine, only one of the strokes is utilized in producing power. The other three are effectively absorbing power, while in the gas turbine engine, the 3 idle strokes have been eliminated, thus allowing more time for the burning of fuel. This is just one of the reasons why the gas turbine engine has a greater power-weight ratio than the piston engine. The pressure-volume diagram shown here, otherwise known as the Brayton cycle, represents the working cycle of the gas turbine engine in its simplest form. Air at atmospheric pressure enters the engine at point A and is compressed along the line AB. Fuel is added in the combustion chambers, which is signified by point B, and the mixture is burnt, in theory at a constant pressure. In fact, the reduction in pressure shown between points B and C indicates that pressure losses do actually occur in the combustion chamber. The drop in pressure is created by the need to produce the swirl and turbulence necessary for efficient combustion, and this causes a pressure drop throughout the combustion chamber length of between 3 to 6%. Notwithstanding this drop, a considerable increase in the volume of the air is generated within the combustion chamber. Between points C and D, the gas generated through combustion expands in the turbine, where mechanical power is extracted from the energy in the gas stream, and the jet pipe, where the remainder of the gas stream energy provides a propulsive jet as it is discharged. In theory, the gas stream pressure attains a value equal to atmospheric pressure before being ejected. As we previously stated, theoretically combustion in the gas turbine engine occurs at a constant pressure. This is achieved partly through the continuous process of the Brayton cycle, and also by the fact that the combustion chamber is not an enclosed space. These circumstances ensure that there are no fluctuations of pressure in the engine as there are in the piston engine, where peak pressures greater than 1,000 pounds per square inch have to be accommodated. These high internal pressures necessitate utilizing extremely strong and heavy construction in the piston engine, and also, if detonation is to be avoided, the use of high-octane fuels. In contrast, in the gas turbine engine, the use of low-octane fuels and relatively light construction methods are the rule, rather than the exception. The turbojet is a heat engine. The higher the temperature attained in combustion, the greater the expansion of the gases, and hence the greater efficiency of the engine. There is, however, a limit to the amount of heat that can be released into the turbine from combustion. This limit is imposed by the materials from which we manufacture the nozzle guide vanes and the turbine blades. The Germans' inability to produce materials which could withstand the heat of the gas stream was the main problem with the early German gas turbine engines. Because of the poor materials used in the turbine assemblies, the engines would only run for between 10 to 20 hours before the turbine blades suffered meltdown and engine disintegration commenced, usually in a quite catastrophic fashion. The use of modern materials and extremely efficient cooling methods in the nozzle guide vanes and the turbine blades has enabled the use of much higher gas temperatures in the latest engines. This has resulted in the more modern engines having a higher thermal efficiency than their predecessors. Gases behave differently from the other two commonly studied states of matter, solids and liquids, so we have different methods for treating gases and understanding how they behave under certain conditions. Gases, unlike solids and liquids, have neither fixed volume nor shape. They are moulded entirely by the container in which they are held. There are three variables by which we can measure gases: volume, pressure, and temperature. We'll discuss two of the so-called gas laws which are most pertinent to the operation of the gas turbine engine: Boyle's law and Charles' law. Robert Boyle was born in 1627 in Ireland. He made important contributions to physics and chemistry, but is best known for the law which was named after him, concerning an ideal gas. Boyle's law states that, in a gas which is held at a constant temperature, the volume of that gas is inversely proportional to its pressure, or pressure times the volume equals a constant. This holds true where P is the absolute pressure of the gas, and V is the volume occupied when the pressure is P. This is a reproduction of an experiment carried out by Boyle. He had a calibrated syringe filled with air and deduced its volume. While taking care to retain the temperature of the air inside the syringe constant, he increased the pressure and decreased the volume inside it by placing weights on its plunger, taking readings as he did so. You can see that by multiplying the volume by the pressure, the answer remains a constant. Hence, the product of the absolute pressure and volume of a given quantity of gas is constant, as long as the temperature of the gas does not change. Try moving the plunger up and down yourself to simulate changing the weight on it, and note that the results of P times V always remain a constant. Because of the interest in hot air balloons in the early 1800s in France, Jacques Charles and Joseph-Louis Gay-Lussac made detailed measurements on how the volume of a gas was affected by its temperature. Just as Robert Boyle made efforts to keep all properties of the gas constant, except for the pressure and volume, so Jacques Charles took care to keep all properties of the gas constant, except for its temperature and volume. Charles' law, or Gay-Lussac's law, states that if any gas is held at a constant pressure, its volume is directly proportional to the absolute temperature, or, if stated as a formula, the volume divided by the temperature is a constant. Just as we did to demonstrate Boyle's law, we'll replicate an experiment similar to one carried out by Jacques Charles. If we partially fill a calibrated syringe with air and place it in a container of water, then by increasing or decreasing the temperature of the water, and thus increasing or decreasing the temperature of the air inside the syringe, while taking readings of the volume and temperature, and then dividing volume by temperature in degrees Kelvin, we see that the answer is a constant. Remember that, in theory, the pressure inside the syringe remains constant also. Try changing the temperature of the water for yourself, and notice that the results of the volume divided by the temperature remain a constant. Although both Boyle's law and Charles' law work in theory, we are unable, with existing technology, to make them work in practice. For instance, it's impossible as yet to increase the pressure of a gas without increasing its temperature, because of the adiabatic heating which inevitably occurs. Remember the example which is consistently quoted of how a bicycle pump always heats up when air is pumped into a tire. By using Boyle's and Charles' law together, we get a practical method of determining what is happening to the gases inside the gas turbine engine, where temperatures, pressure, and volume are all changing constantly. With the scientists' usual lack of imagination, they have named the integrated Boyle's and Charles' law the combined gas law. The combined gas law represents the relationship between volume, pressure, and temperature. This may be shown as P1 times V1 over T1 equals P2 times V2 over T2. The three main stages when these conditions change in the gas turbine engine are during compression, combustion, and expansion. During compression, work is done to increase the pressure and decrease the volume of the air. There is a corresponding rise in its temperature. Just as they do in the piston engine, higher compression ratios give higher thermal efficiency and lower specific fuel consumption. Notice that the velocity of the air as it progresses through the compressor is actually reducing. This is required so that when it gets to the combustion chambers, its speed is not such that it will extinguish the flame. During combustion, the addition of fuel to burn with the air increases the temperature, and there is a corresponding rise in its volume at an almost constant pressure. The velocity of the gas flow continues to reduce through the combustion phase, until the end of the combustion chamber, which, due to its convergent shape, initiates an increase in its value. The reason for this will soon become apparent. During expansion, when some of the energy in the gas stream is being converted to mechanical energy by the turbine, there is a decrease in both the pressure and the temperature of the gas with a corresponding increase in its volume. The changes in velocity over the expansion phase are a little more complicated than in the previous phases. The expansion phase is when the kinetic, pressure, and heat energy in the gas stream are being converted into mechanical energy by the turbine to drive the compressor. The turbine is most efficient at converting the kinetic energy in the gas stream into mechanical energy, and in order to do this, the nozzle guide vanes which precede each turbine rotor stage are shaped to form convergent ducts. At the nozzle guide vane stage, the pressure energy, and to a lesser extent the heat energy, are reduced by the convergent ducts, and converted into kinetic energy, which, as you can see, shows a dramatic rise. The turbine rotor following each nozzle guide vane stage reduces this kinetic energy by converting it, and some of the remaining pressure and heat energy, into mechanical energy. Succeeding nozzle guide vane stages will continue to convert the pressure and heat energy in the gas stream into kinetic energy, and the turbine rotor stages which follow them will convert that kinetic energy into mechanical energy. The gas stream is then directed into the exhaust nozzle, where the velocity decreases at the expense of a small rise in pressure. This decrease in velocity assists in maintaining the losses in the jet pipe due to turbulence at a minimal level. Finally, as the gas passes through the sharply convergent propelling nozzle, the duct shape causes a distinct increase of velocity, and the pressure of the stream drops to that of ambient in response to that increase. As the air passes through the engine, various adjustments must be made to its velocity and pressure. For example, throughout the compression stage, the air must be compressed, but no appreciable increase in its velocity can be easily tolerated. Another example, which we've already seen, occurs at the exhaust nozzle, where the pressure of the gas is dropped to that of ambient, and a considerable increase in its velocity results. These changes in pressure and velocity are accomplished by the different shaped passages or ducts through which the air must pass before it exits the engine. The design of these ducts is extremely important, because the efficiency with which the changes from kinetic energy to pressure energy and vice versa occur are reflected in the overall efficiency of the engine. In this example of the use of different duct shapes within the engine, it can be seen that the use of a divergent duct will increase the pressure of the air after it leaves the final stage of the compressor and before it enters the combustion chamber. This air, sometimes called compressor delivery air, is the highest pressure air in the engine. Using a divergent duct here gives a twofold advantage. First, an increase in pressure has been achieved with no expenditure of energy in driving the compressor. Secondly, a decrease in velocity has been contrived, which will serve to make the task of the combustion chamber, in keeping the flame burning, less difficult. This example, which we've already experienced, shows how a convergent duct is used to accelerate the gas as it passes through the nozzle guide vanes on its way to the turbine blades. The torque which is applied to the turbine blade is dependent, amongst other things, upon the rate of gas flow into it. It follows, then, that the faster we can make the gas flow into the turbine, the more torque we can transfer to the turbine. Logically, therefore, if we convert some of the considerable pressure energy of the gas stream into kinetic energy, it will be more efficient in imparting a turning effect upon the turbine and its shaft. When a compressor and turbine are joined on one shaft, the unit is called a spool. This diagram shows a single-spool axial flow compressor turbojet engine. This type of engine was for a long time considered to be the most useful where an engine with a small frontal area was required, such as in fighter aircraft, where a high forward speed was the main criterion. There are, however, problems with the control of the smooth flow of air through the engine throughout its rotational speed range. More of this later. As it flows from the compressor, the air is fed directly into the combustion chambers, and fuel is added and the resulting mixture ignited. The resultant increase in temperature will cause the substantial increase in volume which is required. The energy required to drive the compressor, approximately 50% of the energy in the gas stream, is now extracted from the stream as it passes through the turbine. The remaining energy in the gas stream acts as thrust, as the gases pass to atmosphere via the end of the jet pipe. This diagram illustrates both a centrifugal compressor turboprop engine and an axial flow compressor turboprop engine. The output from a turboprop engine is the sum of the shaft horsepower developed at the turbine and the residual jet thrust. This is called equivalent shaft horsepower, or ESHP. The major difference between the turbojet and the turboprop in how they handle the generated power is that, in the turbojet, virtually all of the energy that remains after the compressor has been powered is used as thrust. Whereas in the turboprop, almost all the energy in the gas stream is converted into mechanical energy to drive both the compressor and the propeller. Only a small amount of jet thrust is available from the exhaust system of a turboprop with an efficient turbine. It can fairly be described as residual thrust only. Apart from this difference, the airflow through the engines is virtually the same in either case. The compressor passes the air to the combustion chambers where the fuel is added and the mixture is burnt, and because of the temperature rise, a substantial increase in the volume of the air is obtained at a nominally constant pressure. The gas is now expanded in the turbines, where a drop in the pressure and temperature is converted into the kinetic energy which is exchanged for the torque used to drive the compressor, or compressors, and the propeller through its reduction gear. The turboshaft engine can be thought of as a turboprop engine where the propeller has been replaced by a shaft. Turboshaft engines can be used to drive helicopter rotors. They can also be used in applications where a compact supply of electrical power is required, their output shaft being attached to an alternator. This is the type of engine normally used as the auxiliary power unit, or APU, on most modern transport aircraft. Most, if not all, turboshaft engines incorporate a free power turbine. A free power turbine is a turbine that is not connected to any of the compressors. This frees the turbine from the constraint of having to rotate at a speed that suits the compressor, and this gives the turbine a much wider operating speed range. The single-spool turboshaft engine illustrated here has a reverse-flow combustion chamber system. This allows the engine to be much shorter, stiffer, and lighter than it otherwise would be, but does add the requirement for a centrifugal compressor to be used in the high-pressure stage. This allows for the air to be thrown out radially, in order that it can enter the combustion chamber in the correct direction. Other than this deviation, the airflow is similar to that previously described for the turbojet engine, up to the point where it leaves the first stage turbine. The first stage turbine having converted sufficient energy from the gas stream to drive the compressor, the free power turbine converts any remaining energy to mechanical energy, which is utilized to drive whatever is attached to its shaft. The bypass ratio of an engine is defined as the ratio of the amount of air which is bypassed around the hot core of the engine to the amount of air which passes through the hot core. An engine with a bypass ratio in the region of about 1 or 2 to 1 would be considered to be a low bypass ratio engine, whereas an engine with a bypass ratio of around 5 to 1 would be considered to be a high bypass ratio engine. The engine shown here is a twin-spool, low bypass ratio engine. The airflow as far as the end of the low-pressure compressor is identical to that of a pure turbojet. But then the airflow splits into two. An amount, depending on the bypass ratio, will flow down the bypass duct. And the remainder continues into what is the start of the hot core of the engine, the high-pressure compressor. From the high-pressure compressor, the air follows the usual path through the combustion chambers and into the turbine, before it leaves the hot core and rejoins the bypass air in the mixture unit of the exhaust system. The propulsive efficiency of both the low and high bypass ratio engines is much greater than that of the pure turbojet, at the speeds normally associated with jet transport aircraft. The term propulsive efficiency is explained later in this lesson. The specific fuel consumption of both the low and high bypass ratio engines is also much lower than that of the pure turbojet. The experience which was gained by manufacturing and operating the low bypass ratio type of engine proved that engines which dealt with a larger comparative air mass flow and lower jet velocities could deliver propulsive efficiencies comparable to those of turboprops, and, indeed, a higher propulsive efficiency than turbojets operating at normal cruising speeds. The advent of the fan jet engine had arrived. This model of a triple-spool front fan turbojet engine shown here represents probably the most successful early example of this type of engine, the Rolls-Royce RB211. The air enters the intake and passes immediately into the low-pressure compressor, more commonly called the fan. Here, its pressure is raised before it splits, to go either through the bypass duct or into the intermediate pressure compressor, the amount going into either depending upon the bypass ratio. The thrust of this type of engine is almost completely dependent on the relatively cold air going through the bypass duct, which has a high mass and relatively low velocity, hence its high propulsive efficiency. The air which passes through to the hot core, which consists initially of the intermediate and high pressure compressors, has a great deal of energy added in the combustion chambers. But this energy is required to drive all of the compressors, which includes the fan. In fact, it is the rearmost turbine, or the low-pressure turbine, which is responsible for driving the front fan by extracting virtually all of the energy that remains in the gas stream. If it's efficient in doing its job, then there should be only residual thrust remaining where the hot gases emerge from the turbine. We previously explained that thrust is the product of mass times acceleration. It can be demonstrated that the same amount of thrust can be provided either by imparting a low acceleration to a large mass of air, or by giving a small mass of air a large acceleration. In practice, the former is preferred, since it's been found that the losses due to turbulence are much lower and the propulsive efficiency is higher. In this graph, the levels of propulsive efficiency for several different types of gas turbine engine will be shown. The highest propulsive efficiency at low airspeeds is offered by the turbo-propeller combination. However, above about 350 miles per hour, the propeller's efficiency drops off quite rapidly due to the disturbance of the airflow at the tips of the blades. In comparison with the turboprop, the propulsive efficiency of the pure turbojet appears quite poor at the lower airspeeds. As the airspeed increases in excess of 800 miles per hour, however, the propulsive efficiency of the turbojet starts to improve beyond the capability of the turboprop engine to match it, and from then on there is no comparison, the eventual outcome being a propulsive efficiency close to 90%. Cruising speeds in the order of 800 miles per hour are at present out of the reach of most transport aircraft. and this fact means that in the mid-speed range, where most of the world's jet transport aircraft operate, there is a niche for the bypass engine, both low ratio and high ratio. The low and high bypass ratio engines, which includes the ducted fan or turbofan engine, have a propulsive efficiency which fits neatly between that of the turboprop and the pure turbojet. By dealing with comparatively larger mass airflows at lower jet velocities, the bypass engine attains a propulsive efficiency which exceeds that of both the turboprop and the pure turbojet at the speeds normally associated with jet transport aircraft. The use of larger and larger aircraft has meant that more passengers can be accommodated in each flight. Thus, air travel has become less and less expensive for the individual. This concept of using large aircraft works well, as long as the aircraft themselves remain serviceable. If, however, one restricting component, such as an engine, becomes unserviceable on a large aircraft, then the expense involved in keeping 300 or 400 passengers fed, accommodated, and happy becomes exorbitant. Engine manufacturers, in an attempt to minimize the financial burden imposed upon the users of their equipment in the event of its failure, have started to use modular construction methods, which facilitate changing sections of an engine rather than the whole engine. This diagram shows how the engine is split into several modules. This concludes the introduction to the gas turbine engine. The air intake of a gas turbine engine is either built into the airframe itself, if the engine is mounted in the airframe, or is the forward part of the nacelle installation if the engine is wing or rear fuselage mounted. The air intake is designed to provide a turbulence-free supply of air to the first stage compressor of the engine, with the minimum energy loss occurring through the inlet. To enable the compressor to operate satisfactorily, the air must reach the compressor at a uniform pressure, which is distributed evenly across the whole face of the first stage. Thus, the design of the intake duct is vital to the performance of the engine, under all air speeds and angles of attack, if compressor stall or surge is to be avoided. The simplest form of intake is a single entrance, circular cross-section, pitot type. The air normally flows directly through the intake when it's fitted to wing-mounted engines. But it can form an S-shaped duct when used on engines which are mounted at the bottom of the aircraft fin, for example like the Boeing 727 or the Lockheed TriStar, which are shown here. Crosswind takeoffs can cause the airflow through this type of intake to become unstable. The pitot type of intake maximizes the use of ram effect on the air, due to the aircraft forward speed, and suffers only a minimum loss of ram pressure as the aircraft attitude changes. However, the efficiency of the pitot type of engine air intake reduces as the aircraft approaches sonic speed. This is due to the formation of a shock wave at the engine intake lip. The shape of a subsonic intake usually takes the form of a divergent duct. While the aircraft is moving at any appreciable speed, the divergence causes firstly a reduction of the airflow velocity between the lip of the intake and the inlet of the compressor, and secondly an increase of air pressure at the inlet of the compressor. However, while the engine is running on a stationary aircraft, the pressure at the inlet of the compressor is below ambient pressure. This is because the engine compressor is increasing the velocity of the airflow through the intake. As the aircraft begins to move, the pressure within the inlet starts to rise. The ram pressure recovery point is usually reached at between Mach 0.1 to Mach 0.2. As the aircraft's speed increases even further, the ram effect produced by the speed increase, combined with the shape of the inlet, produces more and more ram compression, which causes an increase in the engine compression ratio. This effect generates more thrust without costing any increase in fuel flow. However, as can be seen from this graph, at these speeds the thrust recouped from the effect of intake ram pressure does not cause the net thrust level to reach its original zero speed level. Secondary air intake doors, sometimes called auxiliary inlet doors, are required on certain types of aircraft to allow supplementary airflow to reach the compressor face during high-power operation when that aircraft is either stationary or at low airspeeds. The Harrier is an example of an aircraft which must use high levels of engine power when it has either zero or very low forward airspeed, during vertical takeoff, the hover, or landing. During these periods, the demand of the engine compressor for air is extreme. This particular engine air intake is designed for relatively high-speed flight, and as a consequence is not necessarily capable of allowing in the large mass of air the engine requires when it's running at high power levels at zero forward airspeed. To allow in more air to satisfy the engine demands, up to 16 auxiliary air intake doors have been fitted just behind the lip of the main air intake. At airspeeds below which ram pressure recovery can be achieved, the auxiliary air intake doors are held open by the depression in the intake. At higher forward speeds, when the pressure in the intake is greater than ambient, the auxiliary air intake doors are shut by the pressure differential which has been generated. Supersonic aircraft also require a particular type of air intake, which is sometimes called a diffuser, because the engine compressor cannot handle supersonic airflow. Below supersonic speeds, the intake must be able to recover pressure in the same manner as a subsonic intake. But above supersonic speeds, the intake must be capable of reducing the velocity of the airflow below sonic velocity by the formation of shock waves. One important characteristic of a shock wave is that air flowing through it will be slowed. The task of controlling the shock waves that form on or in the air intake, which is fundamental if we're to efficiently reduce the velocity of the airflow, is undertaken by a supersonic diffuser. The supersonic diffuser can be quite simple or quite complex, depending on a number of factors, among which is included the supersonic speed range of the aircraft. For instance, many jet fighters are not designed for sustained supersonic flight, and can therefore use quite a simple intake diffuser. Some of the earliest types of supersonic aircraft featured a central shock cone, called an inlet cone, which was used to form the shock wave. This form of shock cone can be seen here on the English Electric Lightning. This diagram shows a simple convergent-divergent diffuser. This design works because of the fact that supersonic flow will slow down as it enters a constricted area. You will note that this is the opposite response to that which happens with subsonic flow. Air flowing at subsonic speeds will accelerate through a constriction. We know from the previous lesson that subsonic airflow through a venturi accelerates towards the throat. At subsonic speeds, the air will maintain a constant density, and as a result a pressure wave is set up which causes the air to accelerate through the constriction. However, at supersonic speed, pressure waves cannot move out ahead of the air and cause it to accelerate. Therefore, the air becomes more dense and slows down. This is still all in accordance with Bernoulli's equation, which tells us that if the static pressure increases and the density increases, then the velocity must decrease in order to keep the total energy in the airflow constant. To most people, this tendency of supersonic airflow is more intuitive than what happens in subsonic airflow. The objective of the convergent-divergent diffuser is to slow the airflow to Mach 1 just before the throat of the diffuser. The subsonic flow thus obtained will then slow further as it moves through the divergent section, in fact slowing to well below the speed of sound before it enters the engine. Obviously, the geometry of the diffuser has to be specific to the speed the aircraft is flying. Therefore, if the aircraft is to fly at a range of speeds, some more complex system will be required. Generally, the convergent-divergent diffuser is only suitable for short bursts of supersonic flight, at less than Mach 2, such as on the F-15 fighter shown here. For sustained speeds at or above Mach 2, the convergent-divergent diffuser was modified to use variable ramps to control the airflow into the engine. The angle of the variable throat area intake automatically varies with the aircraft's speed, and positions the shockwave to decrease the air velocity at the engine inlet, and also maintain maximum pressure recovery within the inlet duct. A more elaborate type of diffuser is the center body design. This design has a sharp center body, sometimes called a spike. The spike strikes the airflow, producing an oblique shockwave. The spike will frequently be designed to produce several weak shockwaves rather than one strong one. The inlet geometry is then such that the air is drawn into the engine inlet at right angles to the shockwave. The resulting flow is subsonic, as happens in the simple convergent-divergent diffuser. It's important that the shockwaves do not enter the inlet, because the high-pressure pulses they would create could damage the engine by causing the rotor blades and stator vanes in the compressor to flex. A divergent chamber then slows the airflow further before it reaches the compressor. The position of the spike in relation to its distance ahead of the inlet must vary with the speed of the aircraft. This is accomplished by making the center body position controllable fore and aft in the inlet. It will be extended as the aircraft flies faster and retracted as it slows down. This design is suited to sustained supersonic flight and was used on the SR-71 Blackbird aircraft. The Pratt & Whitney J58 engines fitted to the SR-71 were unable, at high Mach numbers, to carry the large mass of air entering their inlets without stalling their engine compressor blades. At these speeds, the excess air was directed through a bypass system straight to an afterburner. This effectively converted the engine from a conventional turbojet to a ramjet in flight. At very high speeds, the aircraft obtained 80% of its thrust from the ramjet operation, as opposed to 20% from the engine operating as a turbojet. This improved the specific fuel consumption figures by between 10 and 15%. The engine air intake is designed to maintain a stable airflow to the compressor face. Anything that disrupts the airflow and causes it to be turbulent may cause the compressor to stall or surge. An intake operating at high angles of attack cannot be expected to maintain a stable airflow. One of the most critical times for any engine is during its acceleration to takeoff power. If there is any crosswind during the takeoff, it may affect the airflow into the intake, particularly in the case of aft body-mounted engines which have an S-duct type of intake. To avoid the possibility of engine stall and surge, the procedure defined in the operating manual must be followed. Typically for this type of aircraft, that procedure is to allow the aircraft to start rolling forwards on the runway with idle power set, before smoothly opening the throttles to have takeoff power set by approximately 60 to 80 knots. This procedure is termed a rolling takeoff. Intake icing will occur if the ambient conditions are conducive to it. Typically these conditions are 1. An indicated outside air temperature of below plus 10 degrees Celsius. And 2. The presence of visible moisture, that is, fog or any form of precipitation, or alternatively, standing water on the runway, or if the RVR is less than 1,000 meters. In these conditions, the operator should select the engine anti-icing system. Damage to the intake, or any roughness inside the intake, may cause the incoming air to be turbulent, which may disrupt the airflow into the compressor, causing it to stall or surge. It's particularly important to inspect the engine intakes before flight for any form of damage, uneven skin panels, surface roughness, etc. Damage to compressor blades is invariably caused by ingestion of foreign objects. This will most commonly occur while the aircraft is operating on or close to the ground. Damage to the compressor blades leads to changes in their geometry, which can cause performance deterioration, compressor stall, and even engine surge. As well as ensuring on the pre-flight check that the engine intakes are free of foreign objects, particular attention must also be paid to the area on the ground in front of the engine intakes prior to engine start, to ensure that it's free of loose stones and other debris. This is particularly important in the case of wing-mounted engines, which have their intakes close to the ground. It's no coincidence that aft body-mounted engines, whose intakes are above the level of the bottom of the aircraft fuselage, suffer much less with foreign object damage than do wing-mounted engines. Heavy in-flight turbulence can seriously disrupt the airflow into the engines. Using the correct turbulence penetration speed will reduce the possibility of compressor malfunction. It may also be a requirement of the checklist in these conditions to activate the continuous ignition system to reduce the probability of engine flameout. To prevent damage occurring from foreign object ingestion, it's essential that the operators of gas turbine engines should take precautions which preclude the entry of debris into the ramp area. After flight, intake and exhaust covers should be fitted to prevent ingress of contaminants and also help to prevent the engine windmilling. During engine startup, aircraft taxi, and engine reverse thrust operation, debris can be sucked into the intake. Engine power should be kept to the minimum required to avoid damaging it. Several deaths and many serious injuries have been caused through personnel being sucked into the intakes of operating gas turbine engines. Great care must be exercised whenever it's necessary to function in close proximity to running engines. This video is a chilling reminder of what can happen, even when personnel are being extremely careful. This concludes the lesson on air intakes. To increase the efficiency of the gas turbine engine, the air being fed into it must be compressed before it has fuel added to it, and it's burnt in the combustion chambers, and it's subsequently expanded in the turbines. There are two types of compressor being used in engines presently available. One allows axial airflow through the engine, while the other creates centrifugal flow through the engine. In each case, the compressors are driven by a turbine, which is coupled to the compressor by a shaft. The centrifugal compressor is much more robust than the axial flow compressor. That, and the fact that it is the easiest and cheapest of the two types to manufacture, made it the compressor of choice in early gas turbine engines. The centrifugal compressor does, however, have one or two disadvantages, which have relegated it to the second position with regards to its use in large modern engines. Firstly, if we compare two compressors, one centrifugal and the other axial, each having the same frontal cross-sectional area, we would, first of all, find that the axial flow compressor can take in a far greater mass of air than the centrifugal compressor, and secondly, that much higher compression ratios can be attained in the axial flow compressor. Since the amount of thrust generated by a gas turbine engine depends partly upon the mass of air flowing through it, it can be demonstrated that when comparing two engines, each having the same frontal cross-sectional area, the engine which has an axial flow compressor will generate more thrust than the engine with a centrifugal flow compressor. We'll now examine the principles of the centrifugal compressor. The turbine assembly, attached to the compressor by a shaft, converts the pressure, velocity, and heat of the gases passing through the turbine into mechanical energy. which is used to drive the impeller of the compressor round at high speed. Air is introduced continuously into the eye, the centre of the impeller, by rotating guide vanes, and centrifugal force causes the air to flow outwards, across the impeller, towards the tip. Because of the divergent shape formed between the impeller blades, the pressure of the air increases as it flows outwards between them. And, because the turbine is adding mechanical energy into the equation, the air's velocity also increases. The air leaves the tip of the impeller and passes into the diffuser section. The diffuser section is a system of stationary divergent ducts. The ducts are designed to convert the kinetic energy of the airstream, its velocity, into potential energy, pressure. As you can see from the graph, in practice approximately 50% of the pressure rise across the compressor occurs in the impeller, and the other 50% in the diffuser section. The compression ratio of a very efficient single-stage centrifugal compressor would be in the region of 4:1. This means that the outlet pressure of the compressor would be 4 times greater than its inlet pressure. To attain greater engine compression ratios using centrifugal compressors, 2 of them would have to be used in series with each other. In practice, it's not been found feasible to use more than 2 centrifugal compressor stages together. Excessive impeller tip speeds and extreme centrifugal loading prohibit efficient operation of a 3rd stage. As a result of this, engine compression ratios of much greater than 12:1 are not considered possible using centrifugal compressors. We'll now examine the principles of the axial flow compressor, which are basically the same as those of the centrifugal flow compressor. The axial flow compressor converts the velocity of the airstream, its kinetic energy, into potential energy or pressure. The means which it uses to achieve this conversion are, however, different to those used in the centrifugal compressor. The axial flow compressor, an example of which is shown here, consists of a number of stages. A stage embodies one row of rotor blades of airfoil section which are fastened to a disc, followed by one row of stator vanes also of airfoil section. The stator vanes are fastened to the compressor outer casing. The spaces between the rotor blades and the stator vanes form divergent passages. A number of discs, the number equates to the number of stages, are fastened together to form an integral rotor drum, which is driven by a turbine. In the rotor blades, which are turned continuously at high speed by the turbine, mechanical energy is added and converted into both kinetic, velocity energy, and potential, pressure energy. Within the stator vanes, the air pressure is increased by the conversion of the kinetic energy into pressure energy. Essentially, then, the rotor stages of an axial flow compressor can be seen as doing the same job as the impeller in a centrifugal compressor, while the stator stages of an axial flow compressor can be compared to the diffuser in a centrifugal compressor. The pressure rise across each stage is only quite small, the ratio being about 1.1 or 1.2:1. This means that in the first stage, the pressure might only increase by about 3 pounds per square inch. As a consequence of this, in order to achieve the compression ratios demanded by more powerful engines, many rotor stages may be fitted on one shaft, which is driven by its own turbine, as shown here. Assuming that the pressure ratio for each of these 10 stages was 1.2:1, the output pressure for this compressor would be in the region of 91 pounds per square inch. This arrangement, where a number of compressor rotor stages on a single shaft are driven by a turbine, is termed a spool. In larger, more modern engines, compressors may consist of up to 3 spools. So effective is this method of compression that in an engine like the Rolls-Royce Trent, compression ratios in excess of 35:1 can be attained. In this engine, the pressure rise over the last stage may be greater than 80 pounds per square inch. The high pressures generated can result in compressor outlet temperatures of up to 600 degrees Celsius. Although we have only shown engines which have just centrifugal or axial flow compressors, some lower-powered engines do use a combination of centrifugal and axial compressors. The space between the rotor drum and the compressor outer casing is called the air annulus. To maintain the axial velocity of the air reasonably constant as it passes through the compressor, as it's being compressed into a smaller and smaller volume and its density is being increased, the size of the air annulus must be reduced. This gradual convergence of the annulus is achieved by either tapering the compressor outer casing or the rotor drum, or, in some cases, a combination of both is used. Increasing the compression ratio of a compressor makes it progressively more and more difficult to ensure that it operates efficiently over the whole of its speed range. This diagram shows the vectorial relationship between the axial velocity of the air flowing through a compressor and the RPM of that compressor. That relationship gives us the angle of attack over the rotor blade and determines the pressure zones either side of the blade. If the compression ratio of this particular compressor is designed to be 22:1 at 100% engine RPM, then this diagram depicts the volume of a unit of air under normal compression reducing as it passes through the compressor at 100% power. The vectorial relationship between the engine RPM and the airflow axial velocity will give this angle of attack over the rotor blade, and these pressure zones, which are the optimum that would occur at the design point. The design point is that point in the engine's performance criteria where it's operating at its optimum compression ratio, RPM, and air mass flow. The problem which is associated with the compressor operating efficiently over its complete speed range is caused by the fact that the compression ratio of the engine falls as the speed of rotation of the compressor falls, and vice versa. Therefore, when the engine is operating at low rotational speeds, the air is not being compressed so much as at the design point, and the volume which it occupies inside the engine becomes greater and greater. Here the engine has been throttled to 60% of its full power setting, and the compression ratio is now reduced to 11:1. The volume of the same unit of air entering the compressor is larger when compressed only by 11:1 than when it was compressed at 22:1. To get through the compressor in the same amount of time it took when it was compressed at 22:1, the increased volume of air must be moving faster. The changed relationship between the increased airflow axial velocity and the reduced RPM will give a low angle of attack over the rotor blade, which will reduce the size of the pressure zones as shown here. If, on the other hand, the engine is allowed to rotate faster than its design maximum, then its compression ratio will increase accordingly. In this case, the engine is operating at 105% of its optimum figure, and the compression ratio has increased to 24:1. The volume of the one unit of air entering the compressor will reduce further than it would at 100% RPM, because the compression ratio is now 24:1. To get through the compressor in the same amount of time it took when it was compressed at a 22:1 ratio, the decreased volume of air will be moving slower. Once again, the changed relationship between the airflow axial velocity and the RPM will change the angle of attack. But this time, with decreased airflow velocity and an increased RPM, it will generate a high angle of attack over the rotor blade. The reduction in axial velocity happens throughout the compressor. The reduction in axial velocity can reach a point where turbulent airflow and a phenomenon called stall may occur. Stall is a partial breakdown of the airflow through the engine, and is a progressive condition, which, if it's not checked, may produce an event called surge. Surge is a total breakdown of the airflow through the engine, which can, in the worst case, cause the airflow through the engine to instantaneously reverse its direction of flow. Let's examine the phenomenon called stall more closely. We've said that the angle of attack of a compressor blade is the result of the axial velocity of the air passing across it and the rotational speed of the blade. We said that the forces of the air's axial velocity and the engine RPM combine to form a vector, which allows us to find the actual angle of attack of the airflow over the blade. So, a compressor stall can be caused by an imbalance between the rotational speed of the blade and the axial velocity of the air passing across it, which can occur for various reasons, some of which we'll now examine. Use the buttons to increase or decrease the engine RPM and see the effect that has on the blade angle of attack. Excessive fuel flow, which may be caused by abrupt throttle opening during an attempt to gain rapid engine acceleration. The back pressure generated in the combustion chamber may rise to the extent that it will cause a reduction in the axial velocity of the air passing through the compressor. Engine operation either above or below the engine design RPM parameters. Engine overspeed or underspeed will increase or decrease the rotational speed of the compressor blades. Situations which may either increase or decrease the angle of attack to the point where the efficiency of the blade is destroyed, and thus the axial velocity of the airflow is reduced. Turbulent or disrupted airflow to the engine intake. This will reduce the axial velocity of the airflow through the whole of the compressor. Contaminated or damaged compressor components, rotor blades or stator vanes, which will reduce the efficiency of the compressor as a whole. This will cause an increase in the axial velocity of the airflow through the compressor because of the decreased compression ratio. A contaminated or damaged turbine will not be capable of generating the power required to drive the compressor at the correct speed. This will make the compressor incapable of generating a sufficiently high compression ratio, which in turn will mean that the axial velocity through the compressor will increase. Excessively lean fuel-air mixture, which could be caused by abrupt throttle retardation. This will cause the axial velocity of the airflow through the compressor to be increased by the decreasing combustion chamber back pressure. Any of the conditions just mentioned can cause a compressor stall to commence, and as soon as it does, there is a partial breakdown of airflow through the engine. The indications of compressor stall can be any or all of the following. Fluctuations in the engine RPM. An increase in the vibration level of the engine, which can generate noise, which may become audible in the cockpit, depending on whether the engines are wing-mounted or rear fuselage-mounted. And an increase in the exhaust gas temperature, otherwise known as EGT. This latter effect, the increase in exhaust gas temperature, is caused by the fact that there is less air going to the combustion chambers. Hence, there is less air to cool the products of combustion, the exhaust gases. Remember that compressor stall is a progressive phenomenon. It could, in theory, initially occur at just one blade, subsequently worsening to encompass the whole of one stage, and then, if nothing is done to prevent it, it can affect the whole engine. The progressive deterioration of the speed of the airflow through the engine, caused by the stall phenomenon, will eventually cause a complete breakdown of airflow through the engine, which we said was called a surge. In severe cases, a surge could cause an instantaneous reversal of the airflow through the engine, with air being expelled through the engine intake with a loud bang. If surge does occur, the throttle of the affected engine must be closed slowly, and the cause investigated. Surge is most commonly caused by either fuel system malfunction or engine control mishandling. In extreme cases, a surge could inflict such large bending stresses on the compressor rotor blades that they contact the stator blades, with potentially catastrophic results. Apart from the loud noise that usually accompanies a surge, there is a large rise in the EGT, and the resulting loss of thrust may cause the aircraft to yaw. The pilot must always be conscious of the causes of stall or surge if he is to prevent either from occurring. Smooth operation of the throttles, both when advancing and retarding them, will ensure reliable and prompt response from the engine. The pilot must also be very aware of the restrictions which RPM and the ambient density place upon the power plant, and amend engine handling accordingly. Operation of the engine outside the optimum RPM and axial velocity range is inevitable. Although design criteria are, after all, aimed at producing the greatest engine efficiency near maximum RPM, engine operation at power settings below that point has to occur if we are to be able to throttle the engine back from full power. So, engine operation below the maximum power level means that we are committed to altering the rotational speed of the compressor, and also the axial velocity of the air as it passes through the engine. Unfortunately, by doing either of these, we are encouraging the onset of stall and surge. Systems that ensure that surge and stall do not happen have to be fitted to the engine. Here are some of those systems. Variable inlet guide vanes, or VIGVs. Variable stator vanes. Compressor bleeds. Multi-spool compressors. Variable inlet guide vanes, or VIGVs, are fitted to engines which have a particular problem with inherent compressor stall at low RPM or during engine acceleration or deceleration. Variable inlet guide vanes are fitted just in front of the first rotor stage. Variable inlet guide vanes can be automatically pivoted around their own axis to vary the path of the airflow going into the compressor, so maintaining the proper relationship between the compressor rotational speed and the velocity of the airflow through the front compressor stages. At low compressor speeds, the variable inlet guide vanes are angled to impart the greatest amount of swirl to the air, thereby correcting the relative airflow to obtain the optimum angle of attack over the rotor blades. Maintaining this optimum angle of attack allows a smooth and rapid engine acceleration. At high compressor speeds, the variable inlet guide vanes reduce the swirl imparted to the airflow, thereby maintaining the correct angle of attack of the air flowing over the rotor blades. After the first rotor stage has been successfully negotiated, the airflow may still have problems further down the compressor, when the engine is operating at other than its optimum conditions. To minimize those problems, some engines are fitted with variable stator vanes. Variable stator vanes can be pivoted automatically so that as the compressor speed is reduced from the optimum design value, they are progressively closed to maintain the airflow onto the following rotor blades at an acceptable angle of attack. In some engines at low compressor RPM, the relationship between RPM and airflow axial velocity may not be maintained to give the rotor blades the optimum angle of attack, unless some of the excess volume of air is allowed to escape from the intermediate stages of the compressor. If a compressor bleed valve, like the one shown here, is fitted to the compressor casing at a position adjacent to the intermediate stages of the compressor, it can be opened at low RPM and during engine acceleration to allow some of the excess volume of air to escape. This will have the effect of bringing the axial velocity of the air in the earlier stages of the compressor closer to the optimum value, and also of reducing the choking effect in the rear of the compressor. This diagram shows a pneumatically operated compressor bleed fitted to the intermediate compressor section of a bypass engine. When the engine is operating at reasonably high power settings, the high pressure or HP compressor output will be high enough to lift the diaphragm in the actuator valve, allowing high pressure air to maintain the bleed valve closed. Conversely, when engine RPM drops, the high pressure compressor output pressure also drops. Eventually, the drop in pressure will allow the actuator valve diaphragm to fall, and its attached valve to close off the supply of HP air to the bleed valve. Consequently, with its supply of HP air cut off, the bleed valve opens, allowing a reduction in the volume of air through the compressor, which would otherwise tend to choke the flow of air through the engine. This combination of optimum airflow velocity and reduced choking will ensure that compressor stall is less likely to occur during the time the bleeds are open, but there are disadvantages to the use of the system. Opening any compressor bleed, whether it's a bleed used as a stall preventative measure or alternatively a bleed used to supply air for aircraft services, decreases the mass airflow through the engine. A decrease in mass airflow through the engine will cause a drop in thrust for a given throttle position, which raises the engine's specific fuel consumption, or SFC. A decrease in mass airflow also raises the engine's exhaust gas temperature, because the amount of cooling air available in the combustion chambers will have decreased. The design of early axial flow engines was developed by adding more compressor stages on one shaft to obtain higher and higher compression ratios. Unfortunately, having many compressor stages on one shaft makes it increasingly difficult to retain the engine's operational flexibility in terms of being able to operate it over a reasonable RPM range. Compressor blade angles are arranged to give peak engine performance around maximum RPM, when the values of the axial velocity of the airflow and the rotational speed of the blade combine to produce a vector which is the optimum angle of attack of the airflow over the blade. Any reduction of engine RPM changes the symmetry of the vector diagram relating the RPM to the axial velocity. Thus, the angle of attack no longer retains its optimum value. Because of this, compressor stall becomes an ever-present problem at lower engine speeds. So, to overcome the tendency that early axial flow engines had of the compressor stalling at low RPM, designers split the compressor, initially into two separate sections. The two sections were called respectively the high pressure or HP compressor and the low pressure or LP compressor. Subsequently, in later, more powerful engines, designers split the compressor into three sections by adding an intermediate pressure or IP compressor. Each compressor section is driven through a shaft by its own turbine. At any given power setting, the speed of rotation of the compressors increases in proportion to its pressure status. Thus, the intermediate pressure compressor rotates faster than the low pressure compressor, and the high pressure compressor rotates faster than the intermediate pressure compressor. We said earlier that together the compressor, the turbine, and the shaft upon which they are both mounted form a spool. By designing the engine so that, upon closing the throttle, the speed of the low-pressure spool falls off more rapidly than the intermediate pressure and high-pressure spools, it can be arranged that the optimum shape of the vector diagram relating to compressor blade angle of attack can be maintained over a much greater engine RPM range, thus greatly reducing the chance of compressor stall. When referring to the speed of rotation of the spools, it's usual to call the speed of rotation of the low-pressure spool N1, and the speed of rotation of the next spool in the engine N2. If the engine has 3 spools, then the speed of rotation of what would be the high-pressure spool would be called N3. During the development stage of an engine, or more specifically the engine's compressor, a graph will be plotted using data which includes the maximum compression ratio and maximum air mass flow that the engine is capable of sustaining at a particular RPM. A line is drawn which connects points on the graph which equate to the maximum compression ratio and maximum air mass flow at a number of different RPMs. This line is called the surge-stall line. Engine operation at compression ratios or mass airflow values above this line will promote compressor stall and surge. A line is also drawn connecting points on the graph where the engine is operating at RPMs where the compression ratio and the air mass are proportionally matched. This is called the normal operating line. There is a zone between the stall surge line and the normal operating line which is called the stall margin zone. This zone allows for the compressor efficiency reducing throughout its working life, and the inevitable fluctuations which occur in the atmosphere and in the engine fuel system management. Every compressor has an optimum operating point on the normal operating line, which represents just one particular compression ratio, compressor speed, and air mass flow. The optimum point is called the design point. Ideally, the design point occurs on the graph where the engine will spend most of its service life, that is, at cruising speed at altitude. An engine operating at compression ratios, mass airflows, and RPMs that fall below the normal operating line will be operating below its normal efficiency. For instance, throughout its service life, the compressor efficiency will, for various reasons, including minor blade deterioration and contamination, become lower and lower. This will cause the surge stall line to move closer to the normal operating line, reducing the size of the stall margin zone, and thus reducing the tolerance which was initially allowed for those inevitable fluctuations in the weather and fuel system management. This picture shows the basic methods of construction which are commonly used in compressor assembly. The rotor shaft is supported in bearings and is coupled to the turbine shaft in a manner that will allow minor variations in alignment to be catered for. The centrifugal load imposed on the compressor dictates that the rotor blades are fixed to a disc, which itself is fitted around the rotor shaft. The types of rotor blade fixing methods vary, the most common being that where the root of the blade is shaped to form a dovetail joint and secured to the disc by a pin or locking tab. This picture shows dovetail fixing of the blades in the complete disc, with one loose blade in the foreground which utilizes the fir tree type of fixture. The dovetail method of fixing does not ensure that the blade is held immovable in the disc. In fact, the blades are quite loose until firmly seated by centrifugal force during engine operation. Thus, when the engine is windmilling on the ground, the blades rattle loosely and make a sound which is similar to the noise a bag of nails makes when it's being shaken. It's become more and more difficult on smaller engines to design a practical compressor blade fixing method and, at the same time, maintain minimum rotor disc weight. One way of getting over the problem is to produce rotor blades integral with the disc. This type of blade and disc combination is called a blisk. The stator vanes, similar to the rotor blades, are also airfoil-shaped. They are either fixed into stator vane retaining rings, which are themselves fastened to the casing, or they are fixed to the compressor casing directly, as are these shrouded vanes shown here. The shrouding at the inner ends of the stator vanes prevents them vibrating. The vibration can be induced by the velocity of the airflow over them. At the low pressure end of the compressor, the casing is constructed of aluminium alloy. Further down the compressor, the intermediate casing is manufactured from steel alloys. Around the high pressure section of the compressor, the temperature of the air is so high that nickel-based alloys are the only materials capable of withstanding it. The rotor blades are of airfoil section and are normally made from nickel alloys. They are machined to a close tolerance before being attached to the rotor disc. The rotor blades reduce in size from the front to the rear of the compressor to accommodate the convergent shape of the air annulus, as shown here. Some of the low-pressure stages of the compressor, where the temperature of compression is not too high, may have their rotor blades manufactured from titanium. Indeed, as higher temperature titanium alloys are produced, these alloys are progressively displacing the use of nickel alloys in the rotor blades at the high pressure end of the compressor. Early engines used aluminium alloys in the manufacture of stator vanes, but it was found that it did not withstand foreign object ingestion damage at all well. Thus steel or nickel-based alloys, which have a high fatigue strength and are less easily cracked or eroded by impact, are now used in the manufacture of stator vanes. Titanium is occasionally used in some engines for the manufacture of the vanes in the early stages of the compressor, but it is not suitable for the production of the smaller vanes further into the engine, where the high temperatures of compression can adversely affect it. Another problem which may occur is that of blade rub, where the rotor blades come into contact with the compressor casing. If blade rub becomes excessive, which might occur through mechanical failure, sufficient heat from friction would then be generated to ignite the titanium. This would, at best, require expensive repairs, or at worst, cause an airworthiness hazard. The high bypass ratio engine's LP compressor blades, more commonly known as the fan blades, were manufactured in early engines from solid titanium, because titanium combines the properties of strength and lightness. A low blade weight is essential if the fan is to be able to withstand the out-of-balance forces which would occur if a fan blade failed. Despite the enormous strength of titanium, the fan blades had to have a snubber incorporated into their design. A snubber is a support, fitted at mid-span, which prevents aerodynamic instability. Unfortunately, it also adds weight, and particularly when two of them are required, as shown in this picture, they interfere with the supersonic flow characteristics of the air at the extremities of the blade. Experiments with new materials, particularly carbon fibre, were carried out, but its flexibility greatly reduced its effectiveness, and its use has largely been discontinued. The greatest advancement has been achieved by fabricating the blade from a honeycomb core sandwiched between two outer skins of titanium, as is shown here. This method of manufacture gives the fan blade added strength with less weight, enabling the introduction of the wide chord fan blade, which is portrayed here. The stability of the blade is ensured as a result of its wider chord, and therefore the snubber is no longer necessary. Accumulation of contaminants in both the compressor and the turbine section of the engine reduces the efficiency of the unit. The contaminants in the compressor, which are mostly salt and pollution from industrial areas, reduce the aerodynamic efficiency of the blades, which increases the airflow axial velocity, lowering the angle of attack over the blade, as shown in this diagram. In the turbine, the contamination takes the form of sulfidation, which is a build-up of sulfur deposits from the burning fuel. Sulfidation destroys the aerodynamic shape of the turbine blades and the nozzle guide vanes, and will, over a period of time, erode their surface finish. If the major cause of contamination is salt ingestion, as might be the case with an aircraft which flies for long periods low over the sea, like this US Coast Guard C-130, then a timely rinsing of the compressor with fresh water can avoid the use of harsher treatment which otherwise would be required. A compressor rinse can be carried out either while motoring the engine over on the starter or while running the engine at idle speed. This procedure is known as a desalination wash. This picture shows the setup required for washing an engine on another C-130 aircraft. The wastewater in this particular circumstance contains a percentage of cadmium, hence the requirement for a container for the wastewater. If the contamination has reached the stage where a desalination wash is not sufficient, then the application of an emulsion-type surface cleaner may be necessary. The cleaner may be a mixture of kerosene and water, or either solvent-based or aqueous-based cleaner. These are sprayed into the engine intake under the same conditions as the desalination wash. This procedure is known as a performance recovery wash. The turbine can also benefit from a performance recovery wash. For some engines, frequent applications of the emulsion cleaner may justify an extension of their service life. A more vigorous treatment, perhaps more applicable to centrifugal compressor engines, is that of the injection of an abrasive grit into the engine intake while it's running at an idle power setting. The grit takes the form of broken walnut shells. The Americans use the broken stones from apricots. Unfortunately, because the grit is mostly burnt in the combustion chambers, this method does not clean the turbine components as efficiently as does the performance recovery wash. This concludes the lesson on compressors. The combustion chamber, or combustor, must contain the burning mixture of air, which is being passed from the compressor, and fuel, from the fuel spray nozzles, in order to generate the maximum heat release at a substantially constant pressure, so that the turbine receives a uniformly expanded, heated, and accelerated stream of gas. This is not an easy task, but advancements are constantly being made in combustion chamber design to enable more efficient use of fuel with less and less pollution of the atmosphere. Efficient combustion has been made increasingly more important because of the rise in the cost of the fuel, and also the increasing awareness of the aviation industry and the general public of the dangers of atmospheric pollution from the exhaust smoke. There is a limit to the maximum temperature of the gas exiting from the combustion chamber. This is imposed by the materials from which the nozzle guide vanes and the turbine blades are manufactured. The slightest excursion above that temperature limit will mean distortion of the turbine blades and the possible disintegration of the turbine, with probably catastrophic results. Modern turbine and nozzle guide vane materials will allow a gas temperature not exceeding 1700 degrees Celsius when it exits the combustion chamber. Considering that the air which leaves the high-pressure compressor may already have been heated to around 550 degrees Celsius during its compression, we can add sufficient fuel to raise the temperature of the gas exiting the combustion chamber by a further 1150 degrees Celsius, before we exceed the limit temperature of 1700 degrees Celsius. It must also be remembered that the combustion chamber has to be capable of maintaining stable and efficient combustion over a wide range of engine operating conditions. Of course, 1700 degrees Celsius would be the temperature of the gas exiting the chamber with full power selected. Lower power settings would require lower fuel flows, and consequently would generate lower gas temperatures. You'll see from this graph that the air enters the combustion chamber at a slightly slower rate than which it enters the intake of the engine. Speeds of around 500 feet per second are not unusual. The flame rate of kerosene, that is, the speed at which the leading edge of a flame would travel through kerosene vapor, is approximately 30 feet per second. If burning kerosene was exposed to an airstream which was travelling at 500 feet per second, it would be extinguished immediately. So, something must be done to slow down the speed of the airflow after it leaves the compressor, and before it reaches the combustion chamber. Otherwise, the flame would not be sustainable. At this position on the graph, we see how this reduction in the velocity of the air is achieved. The air is slowed down, and, an added bonus, its pressure is increased after it leaves the compressor by passing it through a divergent duct immediately before it enters the combustion chamber. In fact, the pressure attained at this point, at the end of this divergent duct, just before the air goes into the combustion chamber, is the highest in the whole of the engine. The reduction in velocity is still not enough, however. Further decreases must be achieved if the flame is not to blow out. The air is divided after it exits the high-pressure compressor into primary, secondary, and tertiary airflows. We'll now examine each of them. This diagram shows how the air entering the flame tube passes through the snout before being divided to go through the perforated flare and the swirl vanes and into the primary zone. The primary zone is a region of lower velocity recirculation, positioned immediately downstream of the fuel spray nozzle. It's within this zone that stable combustion is achieved. The primary air is approximately 20% of the total airflow coming from the high-pressure compressor and into the combustion chamber. This is the air which is mixed, in a ratio of approximately 15:1 by weight, with the fuel and burnt. By being passed through the flare and the swirl vanes, the velocity of the primary air is reduced, which must happen if the flame is not to be extinguished, and the shape and position of the flare and swirl vanes also starts the air recirculating within the region. The remaining 80% of the output of the high-pressure compressor, air which has not been directed through the snout, goes into the space between the flame tube and the air casing. Some of this remaining air, approximately another 20% of the output of the high-pressure compressor, is allowed into the flame tube through secondary air holes. This air is called secondary air, and it reacts with the primary air, which is flowing through the swirl vanes to form a toroidal vortex. The toroidal vortex stabilizes and anchors the flame, and prevents it being moved through the flame tube away from the fuel nozzle area. The temperature of the gases at the center of the primary zone reaches about 2000 degrees Celsius. This is far too hot for the materials of the nozzle guide vanes and turbine blades, so a further drop in temperature is required before the gases can be allowed to exit the combustion chamber. The remaining 60% of the total air coming out of the high-pressure compressor is progressively introduced into the flame tube through corrugated joints and dilution air holes in the flame tube. This air is called tertiary air. Tertiary air is used to cool both the air casing and the gas exiting the chamber. The type of combustion chamber which we have used to illustrate the interaction of the flame and the cooling air is representative of those which would have been used in an early multiple combustion chamber system. Different methods of keeping the combustion chambers from overheating are used. Some flame tubes have ceramic-coated tiles fixed to a skin on their interior walls. Cooling air passes through the holes in the skin and flows between the skin and the tile, which has a ridged surface. The ridged surface improves the heat transfer between the tile and the air. The air finally enters the flame tube at the front and rear of the tile and forms an insulating film for the tile as it flows over it. Other engine designs use a different method of cooling the air casing, which is called transpiration cooling, where a film of air flows between laminations, which form the flame tube wall, and then exits the laminations to form an insulating film of air within the flame tube. This picture illustrates several other features of the type of combustion chamber which would be used in a multiple combustion chamber system. Although the engine would probably start quite readily with only one igniter operating, most gas turbine engines have two igniters. However, because there are only two igniters, another means of passing the starting flame between the combustion chambers in this type of system has to be found. This is called the interconnector. Immediately after light-up, the flame in the combustion chambers which have the igniters causes an increase in the pressure within those chambers. The pressure differential between a chamber which has a flame in it and those adjoining it which have no flames drives the burning gases through the interconnector pipework. When the burning gases come into contact with any unlit mixture in the adjacent combustion chamber, they ignite that mixture. This process is continued around the engine until the contents of all of the chambers is burning, whereupon the pressures within them are equalized and the flow through the interconnectors ceases. The sealing ring at the turbine end of the combustion chamber allows for elongation of the chamber due to expansion. The chamber is fixed at the compressor end by being bolted onto it, and it cannot expand in that direction. The sealing ring allows the chamber to expand into the nozzle box, which is the portion of the engine immediately preceding the nozzle guide vanes, while maintaining a gas-tight seal between the chamber and the atmosphere. The straight-through flow multiple combustion chamber system was developed from Sir Frank Whittle's original design, which was supplied with air by a centrifugal compressor. The straight-through combustion chamber system was later used on some earlier types of axial flow engines, and is still in use on centrifugal compressor engines such as the Rolls-Royce Dart. The multiple combustion chamber system consisted of a number of the individual combustion chambers, which are shown here. Each combustion chamber consists of a flame tube, which has its own air casing. The combustion chambers are disposed around the engine just to the rear of the compressor section. This picture shows a multiple combustion chamber system similar to that used in the Rolls-Royce Avon, which was a powerful, for its time, axial flow compressor engine used on many different types of aircraft, both military and commercial, fighter and transport, for a considerable number of years. Shown here are the snout, the primary air scoop, the interconnectors, and the drain tubes. The drain tubes allow the drainage of excess fuel from the combustion chambers in the unlikely event of the engine failing to start, an event which is more commonly called a wet start. A wet start happens when the mixture of air and fuel in the combustion chamber fails to ignite during a start. A considerable amount of fuel will have been fed into the combustion chamber during the attempt to start. If that fuel is not removed before the next attempt to start, and if that attempt is successful, the result will be a combination of excessively high gas temperatures in the turbine region and torching, which is the name for a very long, very hot, and very dangerous jet of flame issuing from the rear of the engine. Two means of getting rid of the fuel are open to us. First, the fuel drain system. And second, a method of evaporating the remaining traces of fuel from the combustion chambers, the turbine, and the jet pipe. The fuel drain system utilizes the drain tubes which connect the lowest part of each chamber with the next chamber below it. Fuel remaining after a wet start will attempt to find its own level by flowing from the top of the engine to the bottom chamber. Once in the bottom chamber, the excess fuel exits the engine. Any remaining traces of fuel within the engine must be evaporated. To this end, the engine must be motored over on what is termed a blowout cycle. During a blowout cycle, the engine is turned over by using the starter motor. It's rotated for the time normally allocated to a full start cycle, but with the high-pressure fuel cock shut and the ignition system deselected. Air from the compressor will flow through the combustion chambers, the turbine, and the exhaust system, and assist in the evaporation of any fuel still remaining within. The tubo-annular combustion chamber system, shown here, is sometimes also called the cannular or can-annular system. The tubo-annular combustion chamber system differs from the multiple combustion chamber system insofar as it does not have individual air casings for each of the flame tubes. A number of flame tubes are fitted within an inner and an outer air casing, which makes this system a more compact unit. Notice the position of the igniter plug. This illustration is of a typical example of an annular combustion chamber system. It has only one flame tube, which is contained by an inner and outer air casing. The annular system has several advantages over the multiple combustion chamber system and the tubo-annular system from which it was developed. They are: for the same power output, the length of the annular chamber is only 75% that of a tubo-annular system of the same diameter. There are no flame propagation problems. Compared to a tubo-annular system, the air casing area is less. Consequently, less cooling air is required. The combustion efficiency is raised to the point where unburnt fuel is virtually eliminated, allowing the oxidization of carbon monoxide to non-toxic carbon dioxide. There is a much better pressure distribution of the gases impinging on the turbine, so it has a more even load placed upon it. We stated at the beginning of this lesson that we had to obtain the maximum heat release from burning the mixture of fuel and air in the combustion chambers. To do this, we must use the chemically correct air-fuel ratio of 15:1. Whereas in the piston engine the use of the chemically correct air-fuel ratio of 15:1 would cause detonation and dissociation to occur, in the gas turbine engine it poses no such problem, because there are no peaks of pressure to assist in their generation. The fuel and air are therefore mixed and burnt in the primary zone of the combustion chamber in the ratio of approximately 15 units of air to 1 unit of fuel by weight. The addition of secondary and tertiary air will, however, dilute the mixture, to the extent that the overall ratio may vary from between 45:1 to as weak as 130:1. In the introduction lesson, we stated that combustion theoretically occurs at a constant pressure. In fact, as is shown here, a small loss in pressure does in reality occur as the gas passes from the compressor end of the combustion chamber to the turbine end. This loss of pressure is caused by having to provide adequate turbulence and mixing. Losses vary from 3 to 8% of the pressure at the entrance to the combustion chamber. During normal engine running conditions, combustion is self-supporting. The ignition system is actually switched off as soon as the engine has attained self-sustaining speed. Self-sustaining speed is the speed at which, after start, the engine can accelerate without the assistance of the starter motor. There may, however, be certain engine operating conditions which do require the use of the ignition system. For instance, just such a condition would occur following a flameout, which is extinction of the flame due to various unusual occurrences, such as the ingestion of large quantities of water thrown up from the nose wheels into the engine intakes during takeoff from a heavily contaminated runway. Combustion stability means smooth burning of the mixture, coupled with the ability to remain alight over a large range of air-fuel ratios and air mass flows. This graph shows the limits of those air-fuel ratios and air-mass flows within which combustion will remain stable. The graph shows that combustion stability will occur only between a narrower and narrower range of air-fuel ratios as the air-mass flow through the engine increases. And beyond a certain level of air-mass flow, the flame is extinguished. Outside the ignition loop, which lies within the stable region, it is more difficult to start combustion than it is to sustain it once it has started. Restarting the engine in the air while it's windmilling is called a relight. A consequence of this is that, should the engine flame out at high speed or high altitude, it may be necessary to slow down and/or descend before the engine can be successfully relit. This graph illustrates a relight envelope for an imaginary engine, showing the flight conditions under which it would be guaranteed to relight if it was fully serviceable. The airflow through the engine will cause it to rotate or windmill, so the compressor is supplying sufficient air to support combustion. All that is then required is the opening of the high-pressure fuel cock to deliver a fuel supply, and operation of the ignition system to add the final ingredient, a spark. Operation of the ignition system to supply the spark is achieved by selection of the relight switch. The electrical power to the relight ignition circuit functions independently from that which feeds the normal start circuit. Combustion efficiency is the efficiency with which the combustor assembly extracts the potential heat actually contained in the fuel. This graph shows the combustion efficiency of a modern gas turbine engine across the range of air-fuel ratios which occur during normal operating conditions. Modern gas turbine engines have a very efficient combustion cycle. At high power operating conditions, combustion efficiencies as great as 99% are achievable. And at idle, the systems will still give as much as 95%. The very high combustion efficiency attained in modern gas turbine engines is due in no small part to the fuel spray nozzles which are used in them. These nozzles have the task of atomizing or vaporizing the fuel to ensure that it is completely burnt. This is no easy undertaking, considering the velocity of the airstream from the compressor and the small distance available within the chamber for combustion to occur. Other difficulties occur as a result of the relatively low pressures attainable by the engine-driven high-pressure fuel pump at engine start. The pumps can be of the plunger type or the gear type. The pumps are fitted to the high-speed gearbox, which is driven by the high-pressure compressor shaft. The pumps are only rotating at a minimal speed during initial engine start, and are incapable at that speed of providing the high pressures, 1,500 to 2,000 pounds per square inch, required to give a good spray pattern. At engine start, when there is low engine RPM and low fuel pressure, the fuel spray pattern forms what is known as a bubble. This spray pattern is unable to atomize a fuel jet sufficiently for ignition to occur. As the engine accelerates during the start sequence, the pump rotates faster and builds up more pressure until the spray pattern forms a tulip shape. Atomization is still not sufficient to support combustion. Eventually the pump produces sufficient pressure to shorten the tulip until it touches the orifice. Only now is the fuel jet atomized sufficiently to ensure rapid burning. We've demonstrated then that a small orifice of fixed size will provide a finely atomized spray at high fuel pressures. However, when higher volume fuel flows are needed through larger bore nozzles, the pressures required from the pumps to provide that finely atomized spray become unattainable. Thus, for that type of situation, other methods must be found to sufficiently atomize the fuel at engine start when fuel pressures are low. The airspray system uses a high-velocity airstream to break up the flow of fuel. It requires only relatively low fuel pressures, and can therefore operate using the gear-type pump, which is much lighter than the more sophisticated plunger-type pump. The duplex system, and shown here the duple spray nozzle, effectively use an orifice of variable size. At low fuel pressures, a pressurizing valve closes off the main fuel feed to the nozzle, the only supply coming from the primary fuel line. The primary fuel line feeds the primary orifice, a relatively small hole, which is capable of providing a finely atomized spray at lower fuel pressures. When the engine accelerates during start, fuel pressure builds until the pressurizing valve starts to open. This allows fuel to flow through the main orifice, where it will supplement the spray of fuel from the primary orifice. In the vaporizing tube method, illustrated here, the fuel is sprayed from feed tubes into vaporizing tubes, which are positioned inside the flame tube. Primary air is fed into the flame tube through the fuel feed tube opening, and also through holes in the flame tube entry section. The fuel is turned through 180 degrees, and as the vaporizing tubes are heated by combustion, the fuel is vaporized before passing into the flame tube. This concludes the lesson on combustion chambers. The turbine of a gas turbine engine can be likened roughly to an axial flow compressor working in reverse. The first part of the turbine is a stator section, which is called a nozzle guide vane. The nozzle guide vane directs the air axially onto the blades of a rotor section. The turbine extracts the different forms of energy from the hot gases that flow through it, and converts that energy into mechanical energy, which it uses to drive the compressor and gearboxes connected to it. Gearboxes can be used to operate accessories or, in the case of engines that do not use predominantly jet propulsion to generate their thrust, to power propellers or rotors. The energy available in the gas stream flowing through the turbine takes several forms. There is the heat energy, the potential or pressure energy, and finally the kinetic energy, which comes from the velocity of the gas stream. The conversion of all these forms of energy into mechanical energy means that their values will be reduced as the gas stream passes through the turbine. Nevertheless, having said that, the velocity of the gas in the combustion chamber is lower than the eventual velocity of the gas when it reaches the exhaust unit. During normal operation of the engine, the rotational speed of the turbine may be such that the blade tips travel at a rate in excess of 1,500 feet per second. At the same time, the temperature of the gases driving the turbine can, in a modern engine, reach as high as 1,700 degrees Celsius. The speed of these gases is as high as 2,500 feet per second. That is close to the speed of sound at these temperatures. These factors mean that a small turbine blade, weighing only 2 ounces when stationary, can, while it's rotating at its maximum speed, exert a load along its length which exceeds 2 tons. This tensile loading, coupled with the tremendous heat, causes a phenomenon called creep, which is the stretching of the metal of the blade beyond its ability to reform back to its original length. Whatever materials have been used to produce the turbine, and however carefully the temperature and the rotational speed limits of the engine have been observed, creep will, nevertheless, cause the length of the blade to increase over a period of time and engine operating cycles. A blade will have a finite life before failure occurs. The turbine blades of early gas turbine engines were manufactured from high-temperature steel. Use of this material imposed a stringent limit upon the temperature at the rear of the engine, and because the gas turbine engine is a heat engine, it follows that the power output of such engines was limited as a consequence. The next advance in turbine technology was the use of nickel-based alloys, and these were subsequently superseded by superalloys. Superalloys are a complex mixture of many different metals: chromium, cobalt, nickel, titanium, tungsten, carbon, etc. Blades manufactured from superalloys have a maximum temperature limit of approximately 1100 degrees Celsius, or, if the blades are cooled internally, 1425 degrees Celsius. Traditional metal manufacturing processes produce a crystal lattice or grain in the material. The boundaries of the crystals create a weakness in the structure, and are usually the starting point of any failure. Some turbine blades are manufactured by the process of powdered metallurgy, in which powdered superalloys are hot-pressed into a solid state. The blades thus produced have long, slender crystals, and are very creep-resistant. However, in the search for even stronger materials, a procedure called single crystal casting is now being used in the most advanced engines. This type of blade has been directionally solidified via a spiral selector, which permits only one crystal to grow in the blade. This process virtually eliminates corrosion and creates an extremely creep-resistant blade. Ceramic materials are also being used in the production of turbine blades. Originally, the ceramic was applied as a plasma spray, the coating giving very good protection against a corrosive condition caused by a reaction between the base metals of the blade, the sodium in the air, and the sulfur in the fuel. We have seen earlier, in the lesson on compressors, that the compressor added energy to the gas stream by increasing its pressure. That energy is extracted in the turbine by reducing the pressure of the gases flowing through it. This drop in the amount of the pressure energy occurs both as it's converted to kinetic energy, or a higher velocity in the nozzle guide vanes, and also as it's converted into mechanical energy in the turbine blades, as is illustrated in this graph. We've already seen that the turbine stage consists of two elements, one row of stationary nozzle guide vanes and one row of rotating turbine blades. The complete turbine assembly comprises one or more turbine stages on one shaft, which, if coupled to a compressor, forms a spool. This picture shows a cross-section of a single-shaft, three-stage turbine, similar to that used on the Rolls-Royce Dart turboprop engine. There are certain features shown in this diagram which are worthy of special note. The divergent gas flow annulus affords longer and longer blades to be fitted to each turbine stage moving backwards in the engine. This enables the velocity of the gas stream to be controlled as the gas expands into the large volume available to it. The blade shroud shown here is fitted in an attempt to minimize losses due to leakage across the turbine blade tips. It also reduces the vibration of the blades. The clearance between the blade tips and the turbine casing varies because of the different rates of expansion and contraction of the materials involved. In some engines, an abradable lining is used in the turbine casing area to reduce gas leakage through this clearance between the blade tips and the turbine. But active clearance control can be more effective at maintaining minimum tip clearance throughout the flight cycle. This picture shows its use on an American engine. When a turbine is coupled to a compressor to form a spool, for peak efficiency and to ensure that stall and surge do not occur in the compressor, the spool must rotate at a speed which conforms to the requirements of the compressor. We saw in the lesson on compressors that the optimum speed of the spool is that of its design point. A free turbine, sometimes called a free power turbine, is a turbine which is not connected to the compressor. It's connected only either to the propeller or to the rotor reduction gearbox. The fact that it's not connected to a compressor allows a free power turbine to seek its own optimum design speed, rather than that of a compressor. The free power turbine has further advantages. The propeller of a free power turbine engine can be held at low RPM during taxiing, thereby reducing noise pollution and wear on the brakes. A free power turbine engine requires less starting torque than does an engine where the turbines and compressors are coupled together. A rotor parking brake can be fitted to an engine with a free power turbine. This eliminates the dangers inherent in having propellers rotating in windy conditions on the ground. The power output of a turbine can be increased by increasing its diameter. But this would have two detrimental effects. Firstly, it would increase the drag factor by requiring that the engine be designed to have a large diameter. And secondly, that greater stresses would be imposed because of the greater centrifugal forces created. A more effective method is illustrated in this picture, where an increase in the number of stages which comprise the turbine allows an increase in power output with a reduction in turbine diameter. It's a fact that the efficiency of a turbine blade increases as its rotational speed increases. The losses reduce in proportion to the square of the mean blade speed. Unfortunately, the stresses on the blade increase in proportion to the square of the blade speed. It would seem then that the engine designer is locked into a vicious circle, where any attempt to increase engine efficiency by increasing turbine speed would require stronger blades. This would mean making them heavier, which would create greater stresses on them, and so on ad nauseum. All is not lost, however. The advent of the high-ratio bypass engine, with its much greater propulsive efficiency, means that for a given thrust it can have a smaller diameter turbine. This, to some extent, circumvents the vicious circle problems mentioned previously. The high bypass ratio type of engine shown here consists of three spools. Firstly, we have the high-pressure spool, driven by the high-pressure turbine, which rotates the high-pressure spool at relatively high speeds. Then, to the rear of the high-pressure turbine is the intermediate pressure, or IP turbine, driving the intermediate pressure compressor through a shaft which spins inside that of the high-pressure turbine. Finally, the rearmost turbine is the low-pressure, or LP turbine. It drives the low-pressure compressor, more commonly called the fan, through a shaft which runs inside the high-pressure and the intermediate pressure shafts. Nozzle guide vanes are of aerofoil shape. The space between two nozzle guide vanes forms a convergent duct. Within this convergent duct, some of the potential or pressure energy in the gas stream is converted to kinetic or velocity energy. The turbine blades themselves can be impulse type, which is similar in action to a water wheel, reaction type. These blades rotate as a reaction to the lift they create as the gas stream flows over them, or a mixture of the two types, which is called impulse reaction. This picture shows three end-on views of the combination impulse reaction blade. It illustrates how the shape of the blade changes from its base to its tip. The shape change is accomplished by the blade having a greater stagger angle at its tip than at its base. This gives the blade a twist, which ensures that the gas flow does equal work along the length of the blade, and also enables the gas flow to enter the exhaust system with a uniform axial velocity. Normally, gas turbine engines do not use either the pure impulse or the pure reaction type of blades. The proportion of each type of blade utilized is dependent upon the design requirements of the engine. In general, the combination impulse reaction is more commonly used. Impulse-type turbine blades are used in air starter motors. It's very rare to find pure reaction blades being used. When they are, the nozzle guide vanes are designed to divert the gas flow direction without altering the pressure of the gas. The considerable stress imposed upon the turbine blade and the turbine disc when the engine is rotating at working speed makes the method of fixing the blade to the disc extremely important. The fir tree fixing is the most commonly used system on modern engines. The serrations which form the fir tree are very accurately machined to ensure that the enormous centrifugal load is shared equally between them. The blade is free in the serrations while the engine is not rotating, but during operation the centrifugal force imposed holds it firmly in place. The turbine is a very efficient mechanical device. Nevertheless, it does suffer losses during its operation. On average, the energy loss in the turbine is about 8%. This 8% is comprised of approximately 3.5% from aerodynamic losses in the turbine blades and 1.5% aerodynamic losses in the nozzle guide vanes. The rest is divided fairly equally between gas leakage over the blade tips and exhaust system losses. The maximum temperature that the turbine assembly can withstand limits the thrust or power available. Exceeding the maximum turbine temperature will cause irreparable damage to the engine. Therefore, it's imperative that the turbine temperature is monitored closely. The temperature of the turbine is measured by thermocouples, which are placed in the gas flow somewhere in the turbine assembly, typically after the high or low pressure turbine. The temperature measured at this point would be termed the exhaust gas temperature, or EGT. Other terms that are used to represent the value of the gas temperature around the turbine zone are turbine inlet temperature, or TIT, turbine gas temperature, or TGT, jet pipe temperature, or JPT. The jet pipe temperature is so named because of the position of the thermocouples. They are actually placed behind the turbine in the jet pipe itself. In some modern engines, the thermocouple probes are fitted inside selected fixed nozzle guide vanes to enable temperature to be sensed without the probe being battered by the high-velocity gas flow. As the engine is accelerated to produce more thrust or more shaft horsepower, the exhaust gas temperature will increase in proportion with the extra fuel flow, and vice versa. That completes the lesson on turbines. The exhaust system of a gas turbine engine is an often underrated part of the propulsion unit, yet its design exerts a considerable influence on the performance of the engine. The gases which discharge from the turbine must exit in the correct direction and at the optimum velocity to provide the thrust of the turbojet engine. While in the turboprop engine, where the thrust is provided by the propeller, the turbine gas temperature and back pressure at the turbine are, to a large extent, dictated by the design of the outlet nozzle. The temperature of the gases entering the exhaust system can be between 550 and 850 degrees Celsius. This temperature can rise to as high as 1,500 degrees Celsius if an afterburner, sometimes called a reheat system, is used. The fuselage of the aircraft, if it has the exhaust system running through it, as happens with most jet fighter aircraft, must be protected from these temperatures. This is done by both allowing a clearance between the jet pipe and the aircraft skin, through which air is allowed to circulate, and insulating the jet pipe with some form of fibrous material sandwiched between thin layers of stainless steel. The velocity of the gas as it leaves the turbine can be between 750 and 1,250 feet per second. This is somewhere around 0.5 Mach. If this gas has to negotiate a long jet pipe before being ejected into the atmosphere to provide thrust, a great deal of turbulence will be caused within the pipe. This will lower the efficiency of the engine and reduce its thrust. This diagram shows the basic layout for the jet pipe of an aircraft without afterburners. Although the shape of the jet pipe outer casing appears to be convergent at the point where the gas leaves the turbine, the shape of the volume within the casing is in fact divergent. The divergence is made possible by the insertion of the exhaust cone, a conical-shaped device positioned close up to the rear turbine disc rear face. As well as helping to reduce the velocity of the gases leaving the turbine before they pass down the length of the jet pipe, so minimizing turbulence, the exhaust cone also prevents the hot gases flowing across the rear disc face of the turbine, further reducing disturbance and preventing overheating of the disc. The rear turbine bearing is also supported inside the exhaust cone via turbine rear support struts, which are streamlined by fairings. The fairings also straighten out any residual whirl which may exist in the gas stream as it exits the turbine. This residual whirl would cause additional losses through generating turbulence if it was allowed to pass into the jet pipe. The exhaust gases travel down the jet pipe and finally exit to atmosphere via the convergent propelling nozzle. The convergent propelling nozzle increases the gas velocity to speeds of Mach 1, the speed of sound in relation to the temperature of the gases, in a turbojet engine at virtually all throttle openings above idle. At this velocity, sonic speed, the nozzle is said to be choked. The area around operating gas turbine engines is inherently dangerous to personnel and equipment. This diagram indicates the primary danger zones around the intake and exhaust of an engine similar to the type fitted to the Cessna Citation. The more powerful the engine, the further these zones will extend from the engine. Notice that the gas velocity exiting the engine is extremely high, as is its temperature, although the levels of both drop quite dramatically with increasing distance from the exhaust nozzle. Foreign object ingestion is an ever-present danger to gas turbine engines. This short video graphically illustrates the perils facing both personnel and equipment when they are in close proximity to engine intakes. The area behind an operating gas turbine engine is just as dangerous as the intake area. This short video was staged to show what can happen if the engine exhaust danger area is entered without recognition of the perils involved. In the convergent exhaust duct, the shape of the duct accelerates the gas. In a turbojet, the gas flows at subsonic speed at low thrust levels only. At almost all levels above idle power, the exhaust velocity reaches the speed of sound in relation to the exhaust gas temperature. At this point, the nozzle is choked, which means that no further increase in velocity can be obtained unless the gas temperature is increased. When the gas enters the convergent section of the convergent-divergent nozzle, its velocity increases with a corresponding fall in static pressure. The gas velocity at this point now reaches Mach 1. As the gas flows into the divergent section, it progressively accelerates towards the open exit. The reaction to this increase in momentum is a pressure force acting on the inside wall of the nozzle. A component of this force, which acts parallel to the longitudinal axis of the nozzle, produces the further increase in thrust. Having two gas streams to pass to atmosphere makes the exhaust system of the bypass engine a slightly more complex affair to the essentially simple systems we've examined so far. The low-ratio bypass engine exhaust shown here combines the bypass air and the hot exhaust gases in a mixer unit. The mixer unit ensures thorough mixing of the two streams before they're ejected into the atmosphere. This picture shows two methods which are used to exhaust the cold bypass air and the hot exhaust gases. The top illustration shows the standard method whereby the hot and cold nozzles are coaxial and the two streams mix externally. Greater efficiency can, however, be obtained by fitting an integrated exhaust nozzle, which is depicted in the lower illustration. Within this type of unit, the two gas flows are partially mixed together before their ejection into the atmosphere. This diagram shows relative sound levels from various sources, some of the highest among them being aircraft engines. Although an aircraft's overall noise signature is a combination of sounds which stem from many sources, the principal agent is the engine. Airport regulations and aircraft noise certifications governing the maximum noise level which aircraft are allowed to produce have forced rigorous research into ways of reducing that noise. The most significant source of noise from the engine originates from the compressor, the fan in the high-ratio bypass engine, the turbine, and the exhaust. Although the noises which spring from these various sources all obey slightly different laws and mechanisms of generation, their levels all increase with greater relative airflow velocity. The level of noise from the exhaust is more affected by a reduction in its velocity than the noise levels of either the compressor or the turbine are. It's logical, therefore, to expect that a reduction in exhaust jet velocity would have a stronger influence in reducing noise levels than an equivalent reduction in either compressor or turbine speeds. The relative speed difference between the exhaust jet and the atmosphere into which it is thrusting causes a shearing action. The shearing action, in turn, creates a violent and extremely turbulent mixing pattern. Here, where the turbulence zone is narrow, is where the high-frequency noise is being generated in the mixing pattern. And here, where the turbulence zone has widened, the low-frequency noise is generated. The noise of the exhaust of a pure turbojet is of such a high level that the noise of the compressor and the turbine is insignificant, except at very low thrust conditions. The exhaust noise of a bypass engine drops because of the reduction in the velocity of that exhaust. But because they are handling a much greater power, the turbines and the low-pressure compressor of such an engine generate a higher noise output. In the case of a high-ratio bypass engine, say an engine with a 5:1 bypass ratio, the noise from the jet exhaust has been reduced to such a degree that the noise from the low-pressure compressor, the fan, and the turbine are now predominant. Having reduced the noise levels emanating from the main source, the exhaust, engine manufacturers then concentrated on lowering the levels of noise from the rest of the engine, specifically the fan and the turbine. The use of the type of noise-absorbing material which is shown here in the engine intake and the bypass duct is extremely efficient in reducing noise in those regions. Further down the engine, in the hotter zones, slightly different materials are used to great advantage in the same quest for noise reduction. The disadvantage of the use of these materials is that they add a small percentage in weight, and that their skin friction is slightly higher than the material that would otherwise be used. Together, these factors cause a slight increase in specific fuel consumption. Whereas the modern gas turbine engines could take advantage of the new methods of sound-absorbing materials, aircraft fitted with older, pure turbojets had to find some other system of reducing their noise output. Aircraft can still be seen with corrugated internal mixers and lobe-type nozzles fitted to the rear of their power units. The latter cause the gases to flow in separate exhaust jets that rapidly mix with slower-moving air which is trapped by the lobes. The corrugated internal mixer was most efficient at reducing exhaust noise, but unfortunately it also induced performance penalties that limited its popularity with aircraft operators. This concludes the lesson on the exhaust system. Modern aircraft braking systems, which incorporate anti-skid units and other sophisticated devices, are extremely efficient. However, bad runway conditions can reduce the ability of even the most refined braking systems to the point where they become a liability. The addition of a reverse thrust capability has improved the situation so much that landing a modern aircraft on a wet and or icy runway in crosswind conditions need now hold no terrors for the capable pilot. This diagram compares the stopping distances involved when an aircraft lands on a wet and icy runway with and without using thrust reversal. The usual method of operating the reverse thrust system is to select it immediately the weight of the aircraft is firmly on the main wheels. This method of operation, coupled with the use of spoilers, can reduce the landing distance dramatically without producing friction at the wheel brakes. There are three basic thrust reversal systems presently in use. They are clamshell doors, bucket doors, external doors, blocker doors. All of these types of thrust reversal system are typically operated by hydraulic or pneumatic actuators or motors driving screw shafts. The reversing systems reverse the direction of the gas flow, thereby reversing the thrust. The name clamshell has been applied to this system of reverse thrust because of the shape of the reverser doors, which resembles that of a clamshell. In the clamshell door system, the reverser doors are usually pneumatically operated. They use high-pressure compressor air as the power source. Pneumatic rams move the reverser doors from their stowed forward thrust position to their deployed reverse thrust position. In their stowed position, the clamshell doors cover cascade vanes, which are revealed when the doors move to the deployed state. While they are deployed, the clamshell doors shut off the normal exhaust gas exit, forcing the gas to escape through the cascade vanes in a forward direction, so that the forward motion of the aircraft is opposed by the reverse thrust thus generated. The lower cascade vanes are aiming the exhaust mainly in a forward direction, but they are angled so that the exhaust has an outboard angular component as well. This outboard angular component minimizes the chances of debris and hot gases being re-ingested into the engine intake during the use of reverse thrust. The bucket reverser system is normally hydraulically operated. The rear portion of the engine exhaust pipe is shaped like two halves of a bottomless bucket, which are hinged to enable them to swing rearwards when selected, to deflect the exhaust gas forward. The cold stream reverser, or blocker system, is only used on high bypass ratio fanjet engines. The essential difference between the blocker system and both the clamshell door and bucket reversing systems is that, while the latter use the hot exhaust as the means of reverse thrust, the blocker system, as its name suggests, blocks and diverts the cold bypass airstream only. Operation of the blocker system is initiated, as are the other two systems, by movement of reverse thrust levers in the cockpit. Each engine with a reverse thrust capability has a reverse thrust lever. In the case of the blocker system, the speed and direction of an air motor is determined by operation of the reverse thrust lever. The output of the air motor drives flexible shafts, which open or close the blocker doors, which, by their movement, either expose or cover cascade vanes, which direct the bypass air where it's required. In order that the pilot may have information regarding the position of the reverser doors, some form of warning is fitted. The warning can be amber lights positioned somewhere on the forward instrument array within full view of the crew, or, as is shown here, captions which appear on the electronic centralized aircraft monitoring system. The warnings will be shown whenever the reverser doors are unlocked and away from their stowed, forward thrust position. Like a great number of things which purport to be beneficial, the reverse thrust system can, if wrongly serviced or mishandled, become more of a curse than a blessing. Safeguards have to be built into the reverse thrust system which will protect the aircraft in case of a malfunction or incorrect handling. Other indications regarding the reverse thrust system may be provided: reverser deployed, reverser operating, etc. These indications will be dependent upon the aircraft type. There are 5 safeguards built into the selection of reverse thrust. They are: reverse thrust cannot be selected on an engine until the throttle lever of that engine is at idle. Reverse thrust cannot normally be activated on an aircraft until that aircraft is on the ground. This is achieved through the air-ground logic interlock system. Some Boeing aircraft utilize the radar altimeter to restrict reverse thrust operation to below 10 feet above ground level. Having said that, operation of the reverse thrust system is not recommended while airborne. With reverse thrust selected, engine power cannot be increased above idle power until the reverse thrust doors are in the deployed reverse thrust position. If, while forward thrust is selected, the reverser doors inadvertently move to the deployed reverse thrust position, the throttle will automatically close to idle. If, while reverse thrust is selected, the reverser doors inadvertently move to the stowed forward thrust position, the reverse thrust lever will automatically go to the reverser deploy position. While there is normally no restriction on the upper speed at which reverse thrust can be selected, there are aircraft which have reverse thrust systems fitted that restrict the minimum speed of operation of the reverse thrust system. Earlier, it was described how the reverse thrust was angled forwards and outwards. This was to minimize the chances of debris and hot gases being re-ingested into the engine. There is, nevertheless, a clear danger that, despite the angle of the cascade vanes, if the aircraft is only moving forward slowly or is stationary, the depression in the engine air intake will overcome the impetus caused by the deflection applied to the exhaust gas stream and any associated debris and suck it into the compressor, with potentially catastrophic consequences for the engine. To prevent the likelihood of this happening, the standard operating procedure on some aircraft is to reduce the position of the reverse thrust lever to the reverse idle position at typically 60 to 80 knots. Subsequently, at a speed where it's considered there is no further benefit to be gained from maintaining that idle reverse position, that is, when it's judged that there is no further requirement for a sudden selection of full reverse power, usually at about 50 knots, the reverse thrust lever is returned to the stowed position. Reverse thrust is not normally to be used for ground maneuvering. When the reverse thrust system is in use, engine indications must be closely monitored, in particular the exhaust gas temperature. It should be borne in mind that re-ingestion of the exhaust gases will cause the EGT to increase, perhaps exacerbating a situation where high ambient temperatures are already causing the EGT to be close to its limit. Care must be exercised when increasing reverse RPM that the engines respond symmetrically, as adverse yaw can be induced if they are not. This could be particularly embarrassing when applying full reverse thrust when landing on a slippery runway. There may also be a performance limitation imposed if one engine thrust reverse system is inoperative, as the total reverse capability will be reduced, and on an aircraft with two pod-mounted engines, having one engine thrust reverse system inoperative may mean that the remaining serviceable reverser cannot be operated either, because of the asymmetric effect it would impart upon selection. This concludes the lesson on reverse thrust. In order that we can calculate the performance level of any gas turbine engine, specific symbols are used to denote the pressures and temperatures at various locations throughout the engine. Some of these symbols are shown in this diagram. These symbols vary slightly for different types of engine. We've learnt that thrust is obtained from the reaction derived by accelerating a mass of air backwards, thereby achieving forward thrust. In accordance with Newton's third law, for every action there is an equal and opposite reaction. If we examine the formula, in our case the force we require is thrust, so we can restate the equation in this manner. When W equals the mass of air in pounds, V1 is the inlet velocity in feet per second, and VO is the exit velocity in feet per second. In the case of a turbojet running in a choked condition, there will be the addition of pressure thrust, which will give us this. The power of a turbojet can be measured as thrust. Thrust is displayed on either a P7 or an engine pressure ratio gauge, both of which are thrust gauges. The engine pressure ratio, or EPA, is the ratio of the pressure in the jet pipe of the engine, which we call P7, to that at the intake of the engine, which we call P1. The power output of a fan engine can be shown on a gauge which measures the ratio of the integrated values of the turbine discharge pressure and the fan outlet pressure to the compressor inlet pressure. The output of a turboprop is measured in shaft horsepower, or SHP, produced at the propeller shaft. The engine's torque, or turning moment, is proportional to its shaft horsepower. Torque is displayed on a torque meter. P7, EPA, and torque meters are all covered in engine instrumentation on this disc. Thrust equivalent horsepower, or TEHP, is the unit of power used to describe the power output of turboprop engines, and also some turboshaft engines. In practice, there is always a certain amount of jet thrust in the output of a turboprop engine. The equivalent shaft horsepower of a turboprop engine is derived by adding its shaft horsepower output to any horsepower obtained from its jet thrust. Under static conditions, one shaft horsepower equals approximately 2.6 pounds of thrust. We saw from the earlier equation that thrust was proportional to the mass flow rate of air through the engine, and the acceleration we could impart on that air mass flow. Both the mass flow and the acceleration will be affected by changes in altitude, temperature, and airspeed, which all have a bearing on the efficiency of the engine, and therefore the gas energy available for conversion into either thrust horsepower or shaft horsepower. To be economical, an engine must maintain the ratio of its fuel consumption to either its thrust or its shaft horsepower at as low a level as possible. This ratio is termed the specific fuel consumption, or SFC, of the engine. Specific fuel consumption is measured in pounds of fuel used per hour, per pound of thrust or shaft horsepower. The specific fuel consumption is determined by both the engine's thermal and its propulsive efficiency. The amount of thrust produced by a turbojet is proportional to its RPM. Engines which have either a single spool axial flow compressor or a centrifugal flow compressor, and some engines with a combination of centrifugal and axial flow compressors, have a linear relationship between their RPM and the thrust they develop. This linear relationship is shown in this diagram. Engines which have twin spool compressors have a slightly different relationship between RPM and thrust developed. This happens because optimum compressor blade efficiency and compressor ratio are designed to occur at higher RPMs that are normally utilized during the cruise, where the engine spends most of its working life. The relationship between RPM and thrust becomes non-linear, as shown in this diagram. This diagram illustrates that the highest 30% of the thrust is obtained with the RPM above 90% RPM. The ground idle HP RPM of a twin-spool engine is in the order of 58 to 62%, and the LP RPM idles on the ground at about 25%. In flight, these idle values will be higher because of the windmilling effect caused by the forward airspeed. In a high bypass ratio turbofan engine which is running at an idle power setting, the fan speed, or N1, is 25% of its maximum value. The engine will generate approximately 5% of takeoff thrust at this power setting. The different levels of engine power are nominated by the following terms. Takeoff thrust. Maximum thrust available from the engine. This power setting is normally time limited. Go around thrust. This power setting can be the same as that for takeoff thrust, but it's normally a slightly lower value. Maximum continuous thrust. This power setting is the maximum level that can be used continuously. Maximum climb thrust. This power setting is equivalent to max continuous thrust, and is selected to give the best angle of climb speeds. Maximum cruise thrust. This is a power setting below the value of maximum continuous thrust. Maximum cruise thrust can be used, for instance, if the aircraft has to climb more quickly than normal because of a terrain clearance requirement, or in order to respond to a request from ATC for a higher rate of climb. As aircraft altitude increases, temperature, pressure, and density all decrease. The thrust of a gas turbine engine depends upon accelerating a mass of air rearwards. If the density of that air, and thus its mass, is decreasing with increasing altitude, then the thrust generated by that engine must also decrease as the aircraft climbs. Most sophisticated gas turbine engines, which are fitted in aircraft, incorporate an element in the fuel control unit to reduce the fuel flow to match the reduced air mass flow in the climb. This assists in maintaining a constant engine speed for a fixed throttle position. The fall of temperature with altitude increase has a second effect on engine thrust. Because of this reduction of temperature, the air density does not reduce as much as it otherwise would, under the influence of the pressure drop alone. This, to some extent, compensates for the loss of thrust caused by the reduction in pressure. This compensation continues to have effect until the tropopause, which is at 36,089 feet. At altitudes between the tropopause and 65,617 feet, the temperature remains constant at minus 56 degrees Celsius. Thus, at these altitudes, the thrust is affected by pressure alone. This graph demonstrates that the specific fuel consumption remains almost constant with altitude increase. This is because the fuel flow reduces at about the same rate as the thrust reduces as the aircraft climbs. As aircraft altitude increases and the density of the atmosphere reduces, a turboprop engine suffers a similar loss of power to that of a turbojet engine. We showed earlier that the output of a turboprop engine is a combination of its shaft horsepower and any jet thrust that the engine can produce. These graphs show that at a constant airspeed, both the shaft horsepower and the jet thrust of a turboprop engine reduce with increasing altitude. The result of this is that the thrust equivalent horsepower, which is the combination of shaft horsepower and jet thrust, will also reduce with increasing altitude. This graph shows that the specific fuel consumption of a turboprop engine improves as the aircraft climbs to approximately 20,000 feet, but then it increases again as the aircraft climbs towards 35,000 feet. We've already noted that on a hot day the air density will be lower than the international standard, and thus, as we saw from the simple form of the thrust equation, the thrust developed by an engine running at a given RPM will decrease below the level it would attain on an ISA day. However, because it's hot, the air is less dense, and this means that the load on the turbine, as it attempts to drive the compressor at that given RPM, is less. The engine will thus require less fuel to maintain that RPM. Or, alternatively, the engine will run more quickly if the fuel flow is maintained at the same level. On the other hand, on a day when the ambient temperature is below ISA, the density of the air will increase, and the thrust developed for a given engine RPM will also increase. The load on the turbine will have increased because of the increased density of the air passing through the compressor, so to maintain the given RPM, the fuel flow required will have to be increased. Or, alternatively, if the level of the fuel flow is maintained, the engine will run more slowly. In cold ambient conditions, when the air is denser than ISA, the engine will develop its required takeoff thrust before the limiting compressor RPM and turbine gas temperature are reached. However, opening the throttle any further to take advantage of any extra thrust which may be available will have no effect because of an element of the fuel control unit called the power limiter. The power limiter prevents the compressor output exceeding a set maximum pressure, thus safeguarding the integrity of the compressor casing. Engines which have the ability to achieve takeoff rated thrust at less than full throttle when ambient temperatures are below ISA are called part throttle or flat rated engines. From examination of the simple thrust equation, it would appear that, as the aircraft flies faster, if the exit velocity remains the same with an increasing inlet velocity, the thrust will decrease. However, we know from the air intake lesson that the engine air intake is designed so that as the aircraft forward speed increases, the ratio between the total air pressure at the air's entry to the compressor and that of static air pressure at the air intake entry increases. This increases the mass flow through the engine and the exit velocity of that air from the engine. This effect starts to make its presence felt as the aircraft speed reaches between 0.1 and 0.2 Mach. These graphs illustrate that as airspeed increases, the ram effect into the intake of a turboprop engine causes its shaft horsepower to increase, while its net jet thrust decreases. The overall effect on the thrust equivalent horsepower of these two changes is shown in this graph. This concludes the lesson on engine performance. In conditions of high altitude and/or high ambient temperature, the use of a water injection system can restore the thrust of a turbojet engine and boost the output of a turbopropeller engine. Typically, the water injection system is activated by moving the throttle to the takeoff position. We stated in the introductory lesson that the power output of a gas turbine engine depends upon the mass of air flowing through it and the acceleration imparted upon that mass of air. In conditions of high altitude and/or high ambient temperature, the density of the airflow through the engine, and therefore the mass of that airflow, decreases, causing a reduction of thrust in the case of a turbojet engine, or a reduction of shaft horsepower in the case of the turbopropeller engine. To restore, or as is sometimes the case, boost the power output of an engine, the airflow passing through that engine can be cooled by spraying water into it. The amount of water carried for use in these water injection systems can be large. The Boeing 707 and the DC-8 used to carry approximately 300 gallons of water injection fluid per engine, which had all to be used up during the 3-minute takeoff and climb. This equated to a water flow rate of 100 gallons per minute. The fuel flow through each engine at takeoff was 9,000 pounds per hour, or approximately 22 gallons per minute. This gave a water flow to fuel flow ratio of 4.5 to 1 through the engine during those periods when the water injection was being used. This diagram shows the maximum level of power available from a typical early design turbojet engine. The power from this engine is limited artificially by a component in the fuel control system of the engine. Just how this happens need not concern us here. Notice, though, that 100% of power continues to be available even up to 25 degrees Celsius, which is ISA plus 10. At ambient temperatures higher than this, though, the power available drops off. Now we can see the power restoration curve for the same engine after a water injection system has been utilized to restore the power available from the engine back to the 100% level. The ability of the power restoration system is, however, limited to only perhaps 25 degrees Celsius above ISA. The reason for limiting the thrust restoration of the turbojet engine to that of its flat-rated performance is that, although the mass of the airflow could be increased, with relatively few complications, by increasing the compressor speed, the maximum compressor outlet pressure has to be limited to prevent the engine compressor casing splitting under the excessive pressures that would be generated by using such a procedure. This diagram shows the power curve of a typical early design turbopropeller engine without a power augmentation system operating. Now the power output of the same engine has been boosted by 15% by a power augmentation system. Note that in this particular instance the power augmentation uses water methanol as opposed to pure water. More on this fluid later. In the case of a turbopropeller engine, if the water is injected into the combustion chamber, which is by far the most popular method of water injection, the mass flow through the turbine is increased relative to that flowing through the compressor. In the turbopropeller engine, this increase in the mass flow through the turbine is not used to increase the compressor RPM, and thereby increase compressor output pressure. Instead, the increase in mass flow through the turbine is absorbed by coarsening the pitch of the propeller to increase the mass of air being thrust rearwards, while maintaining the engine rotational speed at no more than the normal maximum. This procedure very effectively increases the shaft horsepower output of the engine. Some centrifugal compressor engines, and also some small American-designed axial flow compressor engines, used a system of injecting the water into the engine intake. Unfortunately, the water distribution was not of the best, and also the quantity of water injected had to be limited, so as not to cause an engine flameout. As we stated earlier, injection of water into the combustion chamber increases the mass flow through the turbine relative to that through the compressor. Because a comparatively lower level of energy is being extracted from the turbine, even though there is an increased mass flow through it, there is a related decrease in the amount of pressure and temperature dropped across the turbine. This means that there is an increase in the amount of energy available either at or after the turbine. This can be used to generate extra thrust, either by driving the propeller at a coarser pitch, in the case of a turbopropeller engine, or, in the case of a turbojet engine, by increasing the pressure at the propelling nozzle. A pure water injection system does have some drawbacks, not least because the water must all be used up on takeoff if it is not to freeze in the tanks as the aircraft climbs to altitude. It's logical to require an injection fluid that does not freeze. Thus, methanol is added to the water. The methanol serves primarily as an antifreeze. By injecting coolant into the combustion chamber, the turbine gas temperature is lowered dramatically. However, if nothing was done to counter this fact, it would lower the amount of power potentially available, because the turbojet is a heat engine, which relies on there being a large temperature drop across its turbine. The bonus obtained by using methanol is that, because it is an alcohol fuel, it burns, and thus adds to the temperature of the gases, raising the turbine gas temperature back to its original level. In order to regulate the amount of heat added, the quantity of water methanol injected into the engine must be carefully regulated. This is accomplished by a water methanol control system. The proportion of methanol added to the water must also be carefully controlled. A ratio of 40% methanol to 60% water by volume ensures that the turbine gas temperature limits should never be exceeded during use of the water methanol system. Thrust augmentation by afterburning, or as it's sometimes called reheat, makes use of the unburnt oxygen which remains in the engine exhaust gases to release more heat energy. This is achieved by injecting fuel somewhere between the turbine and the propelling nozzle and burning it. Afterburning is used to improve takeoff, climb and combat performance. Its use is mainly restricted to military aircraft. The one notable exception to this was Concorde, which was the only passenger-carrying aircraft using 4 high-ratio bypass turbojets with afterburners. Fuel is introduced into the jet pipe through discharge nozzles centrally disposed around the axis of flow. This enables some of the relatively cooler turbine discharge gas to flow along the jet pipe walls, which aids in cooling the jet pipe. This is required because the afterburner flame temperature may be in excess of 1700 degrees Celsius. An afterburning jet pipe is fitted with a variable area propelling nozzle. The area of the propelling nozzle is restricted during non-afterburning operation, and it's opened fully to allow for the increased volume of gas which is produced during afterburning operation. The selection of afterburner is usually initiated by the pilot moving the throttle lever through a detent or gate. Control of the nozzle is automatic. When the fuel from the afterburner is ignited, the pressure in the jet pipe, which is called P6 pressure, will increase. This causes a change in the pressure ratio across the turbine. The pressure before the turbine is commonly called P3 pressure, so the pressure ratio across the turbine is P3 to P6. The variable area propelling nozzle is automatically opened so as to restore the correct P3-P6 ratio. In the combustion chambers lesson, we stated that because the flame rate of kerosene is only approximately 30 feet per second, to prevent the flame in the chamber being extinguished immediately, we had to slow down the speed of the air entering the combustion chamber. In the combustion chamber we used components called the flare and swirl vanes to effect that reduction in velocity. Because of this low flame rate, we must also reduce the velocity of the gas stream through the afterburner, in order that the afterburner flame can remain stable. This is achieved by a diffuser, which is positioned before the afterburner section. When the afterburner is selected, an atomized fuel spray is introduced into the jet pipe through the burners. The atomized fuel spray is ignited by either an electric or catalytic igniter plug, or, in some systems, hot shot ignition. Once combustion is established, the gas temperature increases appreciably. The increase in thrust obtained due to the use of an afterburner depends entirely upon the ratio of the absolute jet pipe temperatures before and after the extra fuel is burnt. If, for instance, we assume a gas stream temperature of 900 degrees Kelvin prior to selection of afterburner, and the temperature of the gas stream rises to 1500 degrees Kelvin subsequent to its selection, then the temperature ratio is obtained by dividing 1500 by 900. This gives us a temperature ratio of 1.666. The velocity of the gas stream in the jet pipe increases as the square root of the temperature ratio. In our case, that is the square root of 1.666, or 1.29. This means that the gas stream velocity will have increased by 29%, and thus the increase in static thrust will also be 29%. As can be imagined, the fuel consumption goes up dramatically when the afterburner is selected, so its use is normally limited to short periods only. This concludes the lesson on thrust augmentation. The inside of a gas turbine engine is, understandably, very hot when the engine is in operation. Air, bled off from various positions on the compressor, is used to lower the temperature of those internal parts of the engine which may suffer from excessive heat. The pressure of the air which enters the engine is raised considerably as it passes through the compressor, and it stays reasonably high as it goes through the turbine assembly. The air bled from the compressor, which is used for cooling the internal components of the engine, is also utilized to pressurize seals, which will increase the efficiency of both the compressor and the turbine. Air bled from the engine compressor is also used to service many aircraft systems. In the modern turbofan aircraft, these may include air conditioning and pressurization, hydraulic reservoir pressurization, fuel tank pressurization, domestic water tank pressurization, thrust reverser actuation, fuel heaters, engine airframe anti-icing. For use outside the engine itself, air typically is bled from two sources. We'll use this simplified diagram to show them. The first source is an outlet on an early stage of the compressor, which supplies a continual low-pressure bleed. This continual low-pressure bleed, when system demand requires, is supplemented by a second source of air taken from the HP compressor through a control component called the high-pressure bleed valve. During high-power operation of the engine, the low-pressure bleed is usually of sufficient pressure to maintain the air conditioning and pressurization system. During low-power operation, the low-pressure bleed pressure will fall, and the high-pressure bleed valve will open to ensure both an adequate pressure and sufficient airflow. The high-pressure bleed valve is invariably scheduled to open when airframe anti-icing is selected. In this situation, the requirement is for hot air and lots of it. We know from earlier lessons that the higher the pressure at the bleed, the higher the temperature of the air. All of the bleed air supply from the engine can be shut off, if required, by the operation of an isolation valve. The isolation valve is operable from the bleed air control panel on the flight deck. The isolation valve will also be closed when the engine fire handle is operated, to isolate that engine bleed air from the rest of the aircraft. This diagram also shows fan outlet air being used in a pre-cooler. The pre-cooler controls the temperature of the bleed air going into the system to an acceptable level. The fan can also be used to supply cooling air to the engine oil system and the constant speed drive unit. The bleed air used to supply the cabin conditioning system is controlled by pack flow control valves, sometimes called pack valves. The pack valves enable the pilot to selectively control the air conditioning system and, in the event of a malfunction, particularly one involving smoke in the cabin, shut off individual conditioning packs. Air conditioning bleeds from main engines or auxiliary power units should also be closed during any ground de-icing operation to prevent toxic fumes entering the cabin. When air is bled from the compressor, it reduces the air mass flow through the engine, which has a detrimental effect on the thrust of the engine. This will be indicated on either the P7 or the engine pressure ratio gauge. Reducing the mass flow through the engine also has the effect of reducing the amount of air apportioned to cooling the combustion chamber. This will have the effect of increasing the exhaust gas temperature. Bleeding air from the compressor reduces the load on the turbine. This will have the effect of increasing engine RPM for a given fuel flow. The specific fuel consumption of a gas turbine engine will increase whenever an engine bleed is opened. Air bled from the compressor for use in the engine is used for internal cooling, for instance, cooling the turbine blades. That air can also be used for sealing bearing chambers and areas either side of the turbine discs. Air has considerable work done on it to raise its pressure as it passes through the engine. To ensure maximum engine efficiency, it's logical to extract the air from as early a stage in the compressor as possible, commensurate with it being able to perform its function. When the air has done its job, it's either dumped overboard or alternatively ejected into the main gas stream at the highest possible pressure, thus achieving a small performance recovery. The main parts of the engine that require cooling are the combustion chamber and the turbine section. We've already discussed combustion chamber cooling in a previous lesson. Here we'll examine the cooling of the turbine section. We know from the introduction lesson that the gas turbine engine is a heat engine. High thermal efficiency is dependent upon high turbine entry temperatures. We stated earlier that there is a limit to the amount of heat which can be released into the turbine from combustion. This limit is imposed by the materials from which the turbine blades and nozzle guide vanes are manufactured. If turbine blades and nozzle guide vanes are continuously cooled, then the temperature of their operating environment can exceed the melting point of the material from which they are made. The turbine discs are also heated by conduction from the turbine blades. Thus they must be cooled if their disintegration from the effect of continued thermal stress is to be avoided. Some modern turbofan engines use cooling air to control turbine blade tip clearance. This system, which is shown here, is called active clearance control. It works by controlling the temperature of a tubular shroud which is fitted closely around the turbine casing. A feature of some engines is the selective cooling of the compressor rotor using bleed air. Air extracted from the intermediate pressure compressor to cool and seal the low-pressure turbine discs flows axially through the annular passage between the high-pressure compressor discs and the intermediate pressure compressor drive shaft. This air picks up heat from disc surfaces and the shroud. This assists in controlling the thermal growth of the compressor blades, which increases compressor efficiency. This series of diagrams shows the development of turbine blade cooling since its inception. In the manufacture of early gas turbine engines, it was considered sufficient to pass low-pressure compressor air through the turbine blade. This was called single-pass internal cooling. The use of single-pass internal cooling retained the temperature of the turbine blade below the critical level at which excessive creep would occur. The requirement for greater engine power and efficiency meant that higher gas temperatures were necessary in the turbine. Low-pressure compressor air was no longer able to provide the required amount of cooling on its own. A supplementary source of cooling was required. Research showed that by passing high-pressure compressor air through the blade as well as the low-pressure air, a reasonable increase in the gas temperature could be achieved before blade failure was experienced. This method of cooling the blades was called multi-feed. An additional increase in turbine gas temperature was attained by passing air through small holes in the leading and trailing edges of the blade. This film cooling created its own boundary layer effect. To some extent, this boundary layer protected the turbine blade from the onslaught of the hot gases coming from the combustion chamber. The process involved in cutting the small holes in the leading and trailing edges of the blade is quite intricate and involves the use of industrial laser technology. This video may give you some idea of the operation. This was the type of turbine blade which engines used for the following decade. Eventually, however, events dictated that further advances in blade technology had to be made. Engine designers and researchers reasoned that if passing air through the blade once could lower its temperature, then passing the air through more than once would lower it more. This proved to be true. Eventually, the optimum number of times the air could be passed through the blade was found to be 5, quintuple pass, and the quintuple pass multi-feed internal cooling with extensive film cooling is presently considered to be state-of-the-art in turbine blade manufacture. The nozzle guide vanes use a similar method of cooling to that which is used to cool the turbine blades. The one major difference is that only high-pressure compressor air is used. This diagram shows a nozzle guide vane which is cooled by air from the high-pressure compressor, which is supplemented by film cooling. In the vast majority of gas turbine engines, the turbine blades are fixed to turbine discs. Heat conduction from the turbine blades to the turbine disc requires that the turbine discs are cooled and prevented from suffering thermal fatigue from uncontrolled expansion and contraction. This diagram shows how the front and rear faces of each of the turbine discs is cooled by high-pressure compressor air, the actual pressure in each disc cavity being controlled by interstage seals. More on interstage seals momentarily. To prevent the leakage of oil or air into spaces where it should preferably be excluded, several different types of seal are in current use. Most of these seals work on the principle of the labyrinth, which is another name for a maze. The labyrinth seal consists of fins which rotate within an annulus of oil, or, where the exterior of the seal is static, the annulus can consist of either a soft, abradable material or a honeycomb structure. In the case of the abradable material or honeycomb structure, initial running of the engine makes the fins rub against the annulus material, cutting into it to give the minimum clearance. Interstage seals are used to either prevent or control leakage of air between sections of the engine which are operating at different pressures. During operation of the interstage labyrinth seal, there is a pressure drop across each fin, which results in a restricted flow of air from one side of the seal to the other. The amount of pressure dropped across the seal depends upon the number of fins over which the air must pass. To create two adjacent zones in the engine, one at a higher pressure than the other, we use an interstage seal which has fewer fins in the access to the high pressure zone than are used in the access to the lower pressure zone. More pressure will be dropped by the air passing over the 5 fins before the low pressure zone than will be dropped over the 2 fins preceding the high pressure zone, shown in this diagram. Where seals have to be placed between 2 rotating shafts, it would be possible, if abradable material was used in the manufacture of the seals, that there would be friction between the fins and the abradable material due to flexing of the shafts. This would create high temperatures and the possibility of shaft failure. An intershaft hydraulic seal, like the one shown here, can be used to provide the seal without risking the sort of problems just mentioned. The intershaft hydraulic seal is an example of the first type of labyrinth seal mentioned in this lesson. The fin, or fins, rotate close within an annulus of oil. Any deflection of the shaft will cause the fin or fins to enter the oil, and the seal will be maintained without generating any undue friction or heat. We stated earlier that, to maintain the efficiency of the engine as high as possible, the air required to perform the cooling and sealing functions was taken from as early a stage as possible in the compressor. In the particular case of the air used to seal bearing chambers, that air is taken from the intermediate stages of the compressor through air transfer ports in the compressor rotor drum, and passed through communicating passages to where it's required. The efficiency of all of these seals depends basically upon two factors. Firstly, the mechanical design of the seal, and secondly, the air pressure, which is essential if it's to work at all. Oil loss from a serviceable engine working at high power settings is almost negligible. It's during periods of low engine power, for instance, use of idle power during descent from high altitudes, that the greatest oil loss from a serviceable engine is suffered. If a go-around is initiated after a long stable descent with idle power set, then the engine often shows evidence of great amounts of oil being burnt and ejected with the exhaust. When cooling and sealing has been carried out, the air which has been doing the job has to be disposed of. This diagram shows that the high-pressure air used for cooling is ejected into the exhaust stream. The low-pressure air, on the other hand, is fed out through its own dedicated vent pipe. On some engines, the temperature of the air exiting through this vent pipe is monitored to give an indication of the integrity of the engine's internal construction. Any failure which causes the temperature to exceed a predetermined maximum triggers a warning via a temperature sensor. The warning consists of a red light with the caption IEOH, which stands for Internal Engine Overheat. The response to the warning is a mandatory engine shutdown. This concludes the lesson on engine air bleeds. The accessory gearbox provides the power for hydraulic, pneumatic, and electrical systems which are used on both the engine and in the aircraft. The accessory gearbox is also used to drive fuel pumps, oil pumps, and tacho generators and various other devices necessary for efficient engine operation. The drive for the accessory gearbox is usually taken from the high-pressure compressor shaft via an internal gearbox. The drive then passes to an external gearbox, which provides mountings for the accessories and also, in the majority of cases, the engine starter motor. This picture shows accessory mountings on an accessory gearbox which have been blanked off temporarily. In a modern turbofan engine, there is much less of a problem regarding where to fit the accessory gearbox than there would be in the case of the sleek, slimline type of engine which might be fitted in a fighter aircraft. The turbofan engine itself is so massive that even the largest accessories can be fitted beneath the cowling that forms the air intake fairing. Axial movement of the compressor shaft would cause the teeth of the bevel gears to move apart and the drive would be interrupted. Momentary interruption of a drive transferring 400 to 500 horsepower would impart massive damage to the teeth of the bevel gears and probably destroy them. This state of affairs obviously cannot be allowed to exist. However, axial movement of the compressor shaft must occur due to expansion and contraction during the working cycle. Some method of arranging the gears so that they do not disconnect themselves because of axial movement of the shaft has to be found before a reliable drive unit can be manufactured. This diagram shows one of the methods currently in use to pass the drive between two shafts on modern engines. If the compressor shaft is splined, then a stub shaft, which has teeth cut internally that conform to the pattern of the grooves in the compressor shaft, can be fitted around the compressor shaft. The fact that the spline shaft can move axially while the stub shaft is held firmly in the correct position by the location bearing means that the gear teeth will not lose contact with each other. An alternative system to the stub shaft drive, which will allow the drive to pass between two shafts, uses an idler gear shaft, which is held firmly in position by location bearings. One end of the idler gear shaft terminates in a wide-toothed spur gear, which can accommodate axial movement of the compressor shaft and the spur gear carried on it, and the other end is fitted with a bevel gear, which meshes with the radial drive shaft. In an effort to spread the load of driving accessories, some engines divide the accessory gearbox into two smaller separate gearboxes. As well as the drive from the high-pressure compressor shaft, a second radial shaft is taken from the low-pressure compressor shaft, which is rotating at a slower speed, and used to drive a second external gearbox. This two-gearbox system has a second advantage of allowing the accessories to be divided into two smaller groups, thus overcoming the difficulties of limited space around the engine. During engine start, the starter motor, which is mounted on the accessory gearbox normally driven by the high-pressure compressor shaft, has reversed the normal drive situation. Instead of the gearbox being driven by the engine, the gearbox is now the driving force on the engine. The starter motor thus causes the high-pressure compressor shaft to rotate, and the low-pressure compressor shaft is rotated subsequently by air being drawn through the engine. This generates a situation that requires that accessories which are specific to the engine's operational needs, such as the oil pumps and the fuel pumps, are grouped on the gearbox which is driven by the high-pressure compressor shaft. This gearbox is classified as being the high-speed external gearbox, because it's being driven by the shaft which is rotating at the highest speed of all. Logically, the other accessory gearbox is called the low-speed external gearbox. Having to fit the gearbox around the engine means that the accessory gearbox must have a banana-like shape. For ease of access during servicing, the accessory gearbox is usually located on the underside of the engine. This picture shows an accessory gearbox and some of the associated accessories. Worthy of interest are the oil pumps, which are contained in an oil pump pack, a unit which contains one pressure pump and a number of scavenge pumps. In some engines, as many as 6 scavenge pumps may be contained in an oil pump pack. The width of the gear teeth in this gearbox indicates that the greatest load from driving the accessories is taken on the right side of the gearbox, while the thinner teeth on the left side gear wheels show that their load is much smaller. This grouping of small and large gears enables an efficient distribution of the drives for the minimum weight. Mechanical failure of an accessory could possibly cause the failure of the whole gearbox, and because the engine fuel and oil pumps are driven by that gearbox, the associated engine will fail. To prevent this happening, the mechanical equivalent of an electrical fuse is fitted to some of the accessory gearbox drives. A weak section is machined into the drive shaft. This weak section is known as a shear neck. The shear neck is designed to fail if it incurs a load which is perhaps 25% in excess of the normal maximum load for the particular component being driven by that shaft. In circumstances of excessive overload, the shear neck will break, allowing failure of the individual component, while the rest of the gearbox and accessories continue as normal. This feature is not utilized in the drives of primary engine accessory units, such as the oil pump pack or the engine high-pressure fuel pumps, because any failure of these components would necessitate the immediate shutdown of the engine. This concludes the lesson on gearboxes.